October 25th entered history as the month when, for the first time in human history, two completely independent and initially dissimilar celestial objects simultaneously approached the Sun, each following its own unique path. These astronomical phenomena, which previously seemed incredible and nearly unreachable for human observation, have now become a reality, raising numerous questions and amazement among scientists, enthusiasts, and seekers of new knowledge. Among them, a special place is occupied by the three asteroid-comet trans-Neptunian object, or, as they are also called in scientific circles, the three ATCs, as well as a confirmed interstellar wanderer named Atlas. This last object possesses such a chemical composition that its presence in our solar system violates all existing models and laws related to star formation and planetary development. At the same time, another object, SWR2, rapidly increased its brightness to such levels that it indicated an extraordinary composition, unmatched among all known objects in our own orbital cloud. Their simultaneous approach to the Sun creates a true cosmic jam, like a giant cork, which, according to mathematicians' calculations, should occur once every few million years. And suddenly, to all of humanity's surprise, these two objects found themselves here, in our system, planning to approach the sunlight over 38 days. Earth inhabitants and international space agencies are carefully tracking their trajectories, which, despite their apparent complexity, converge with mechanical precision. All equipment detects chemical anomalies that astonish researchers, as they challenge even decades of comet and asteroid studies, revealing new facets of cosmic secrets. However, precisely at the moment when both objects plunge deeper into solar radiation, our most powerful telescopes will completely lose sight of them, as the most critical moment of their approach will occur. When they vanish from view, as if dissolving into the sunlight. And what if everything happening is not a coincidence? What if someone or something is deliberately preventing us from observing this? Stay with me, because right now we are beginning an in-depth investigation into why October 25th could become a turning point in our understanding of space, in grasping what is truly happening beyond our planet. This is only the first part of our story. Let's look at the sky and record the two bright lights that appeared there simultaneously. Two strangers have shone in the sky, arriving from distant corners of the universe, each with its own story and unique characteristics. The first is a slender and very fast object emitting a green glow that seems alien and extraterrestrial, as if it came from other worlds to observe us. The second, imposing and vivid, with a long tail spreading across several degrees of the sky, creating the impression that it stretches over a vast distance. These two cosmic travelers came from different parts of the universe, from different corners of space, yet they found themselves on the same orbit, converging toward our Sun in what is called cosmic choreography. This astonishing scene causes astronomers to double-check their calculations, as such a coincidence defies conventional expectations. The first of these is an object that materialized on July 1, 2025. In the digital images captured by the ATLS telescope, it appeared as a single bright pixel, which should not have been there before. Although initially it seemed to be just an error, orbital mechanics soon revealed that everything was much more complex. This object, designated Atlas, was moving along a hyperbolic trajectory, clearly not associated with our Sun. It was an interstellar wanderer, the third confirmed visitor from beyond the solar system, whose nature and origin remain a mystery. Just a few months later, the second appeared. Its rich green hue is barely noticeable against the surrounding cosmic space, but to seasoned eyes, it is recognizable and easily distinguishable. This color seems hidden within its composition, and only those well-versed in spectral features can accurately determine its nature. Thus, after sunset, an unusual luminous spot appears on the western horizon, which from afar resembles a bright, descending tail directed upward and sideways, as if painted on the darkening sky with a cosmic brush or an artist's stroke, capturing something extraordinary. This is Swan Earth 2, an object dominating the evening panorama, attracting attention with its mysterious glow. Its tail, like some cosmic canvas, stretches upward, creating the impression that it merges with the dark abyss of night, painted in a deep hue. Inside its structure, instruments operate, transmitting signals on frequencies inaudible to the human ear. These devices, like numerous eyes and ears, detect the slightest vibrations, click the shutters of photon matrices called CCD cameras, which capture light photons, particles of energy traveling millions of years through space to reach us at last. These photons are like messengers of time, carrying information about distant worlds and events that occurred millions of years before our birth. In spectrographs tuned to decompose light into its components, electronic signals whisper, separating and analyzing each spectral line to determine the chemical composition of this mysterious object. Around the world, ground stations scattered across different continents transmit the data they receive to information processing centers, transforming a stream of digital signals into an endless whirlpool of data flowing through channels and cables, much like rivers carrying information about events happening in the distant corners of the universe. In these analytical centers, scientists and engineers work tirelessly, often through long hours and sometimes overnight, tackling the challenges of interpreting and understanding the received information, delving into the subtle nuances hidden behind lines of code and graphs. At the same time, space itself remains silent. The vacuum between stars is a space devoid of air and sound waves because sound simply cannot propagate in such silence. The only bridge between cosmic worlds is electromagnetic radiation, light, radio waves, and other forms of waves that carry information about what occurs beyond our planet's boundaries. It is precisely these light waves, transmitting encoded signals, that tell us these objects are not what they seem at first glance, revealing secrets and features that can only be uncovered with modern technology. One such object is the asteroid, moving at a purposeful speed, suggesting it knows where it is headed and follows a strictly defined trajectory. This trajectory leads it toward our Sun, and as calculations show, its journey will end on October 29, 2025. On that day, it will come within 35 astronomical units of our star, just inside Mars' orbit, so close that its appearance in our cosmic field of view can be considered almost a visit to our own solar system. For an interstellar visitor, such a close approach is a rare and remarkable event. Its path, as expected, is precisely calculated, and it adheres to its own schedule. It reached perihelion, the closest point to the Sun, on September 22, 2025, descending to a distance equal to half an astronomical unit, then began its return journey, moving away from the star. But the most intriguing events occur later. Its closest approach to Earth is planned for October 21st, when it will pass at just 3/10 of an astronomical unit from our planet. The development of comet tails is a process that, on one hand, seems familiar because it repeats general patterns described by many observations and theories, but on the other hand, amazes with its unpredictability and uniqueness, as if following some mysterious scenario written in a language resembling a foreign tongue. In space, scale holds special significance, determining how large or small objects are and how they interact. In this context, the contrast between our cosmic visitors, comets, seems especially vivid and dramatic, as each of them demonstrates its unique nature and behavior, creating the impression that we are observing scenes unfolding in quite different realities. For example, 3 comets appear as if beams of light, focused, compact, and purposeful. According to the latest estimates, the nucleus of this object measures only a few kilometers in diameter, which, compared to the sizes of comets, seems modest, yet is sufficient to generate the activity we observe. These small, seemingly modest bodies, nonetheless, exhibit vibrant dynamics, creating bright tails and light effects that draw our attention. In contrast, SW spreads across the sky like a luminous trail extending over vast distances, resembling a glowing path leading to its source. Its comet, along with its tail, covers significant angles when observed from Earth, creating the impression that the sky is dotted with these glowing threads stretching from space. October 2025 arrives, an especially significant time when 2 such visitors appear in the sky, seemingly rushing toward their closest encounters with our Sun. Mars, the red planet, will take a front-row seat to observe the 3rd comet, which on October 3rd will approach within about 30 million kilometers, quite close for interstellar objects. Our robotic messengers, orbiting Mars and equipped with cameras and spectrometers, will direct their instruments at this approaching visitor, gathering valuable data. Ultimately, this information could help answer many questions that constantly arise among scientists with each new observation, as every encounter with such objects is not only an opportunity to learn something new but also a test for our technologies and theories. However, October brings not only hope but also certain challenges. As the comet and asteroid approach their closest points to the Sun, the geometry of observations from Earth becomes increasingly complex and tangled. The sunlight, which brightly illuminates these objects during this period, will eventually engulf them, leaving our ground-based telescopes completely blind at the most critical moments of their journey. For weeks, or perhaps months, we risk losing sight of them entirely, losing the ability to acquire new data and observations. The question that constantly arises at this moment is, what will happen when these objects, having emerged from the influence of sunlight, reappear on our horizon? Will they remain unchanged, bearing only traces of solar collisions and heats? Or perhaps they carry deeper and more astonishing evidence, revealing secrets that challenge our conventional understanding of cosmic travelers? Perhaps they contain messages or signs of something far more significant than just comets or asteroids, answers to questions we haven't even realized we're asking. These October nights are like a field of mysteries that seem simple on the surface but possess incredible complexity beneath. The question that concerns many scientists and astronomers is the comet we see just a fortress of ice and rocks, or perhaps it holds the key to deciphering messages sent from afar? Every clear, cloudless night on Earth, millions of automated telescopes and sensors continuously gather vast amounts of data about outer space. Within this endless stream of information, millions of star positions are recorded with astonishing precision, allowing astronomers to observe even the tiniest changes in the night sky. It is from this rich dataset that the possibility arises to discover something unusual and unexpected, an interstellar visitor that appears among familiar objects as a single bright flash, standing out from the overall flow. This object moves too quickly for typical celestial bodies, and its trajectory does not match standard paths, drawing particular attention from specialists. However, it is important to understand that ATLAS is just one voice in a global network of automated space monitoring systems. This network includes major projects like the Catalina Sky Survey in Arizona, Leonor in New Mexico, as well as numerous observation complexes located high above Earth's atmosphere. All these institutions contribute to creating an invisible network of eyes that never close, never blink, and are always attentive to any changes in the cosmic environment. Thanks to this coordinated effort and continuous monitoring, scientists today can detect even the tiniest signs of unusual cosmic phenomena. When a sudden and unusual signaling event appeared in data from the solar and heliophysical observatories, it was not NASA professional astronomers who noticed it, but amateurs and enthusiasts, among whom was Vladimir Bezugly. By studying images with his own equipment and analyzing data obtained through modern technologies, he observed something anomalous, a faint but bright glow that ultimately turned out to be one of the brightest and most impressive comets of the 25th century. This is how modern astronomy works today. Professional scientists and amateurs, using silicon sensors, sophisticated instruments, as well as human intuition and instinct, come together as a unified team. They strive to catch those moments when something new and previously unknown appears in our cosmos, something capable of changing our understanding of the universe. Devices installed in various systems whisper their secrets in the language of photons and their intensity peaks. These whispers require a careful human ear to understand when and what unusual event they are trying to tell us about. Each type of instrument reveals a part of the truth about cosmic objects. Cameras operating in the visible spectrum show us the overall structure of a comet, its glowing nucleus, the expanding cometary tail, which usually points away from the Sun, resembling a cosmic fan. But to understand the true nature of these objects, it is necessary to split the light into its components, the colors it consists of. Spectroscopy helps with this. It transforms light into information, which becomes the key to solving the mystery. When molecules in the comet absorb solar radiation and re-emit it, they create unique fingerprints in the spectrum, so-called spectral lines. These lines allow us to determine the chemical composition of the comet and even detect the presence of rare elements. Recent observations conducted with the Large Telescope fan revealed unexpected details. Bright emission lines associated with cyanogen substance were found in the spectrum, and even more surprisingly, signatures of nickel atoms were detected. The appearance of nickel in the comet's composition is unusual, as this element is rarely found in comets and is considered quite rare. Moreover, what makes the situation even more mysterious is that the fan did not record iron emission lines, which typically accompany the presence of nickel in natural samples. The absence of iron combined with the strong presence of nickel creates a unique chemical fingerprint that does not match the usual understanding of how comets form and evolve. Images obtained using specialized devices known as spectrometers of the Internal Spectral Observation Instrument provide a unique opportunity to look at cosmic phenomena from a new perspective. In particular, the device installed at the Solar Geophysical Observatory is capable of recording the distribution of hydrogen atoms in the surrounding space. These atoms are formed as a result of water molecule dissociation caused by ultraviolet radiation from the Sun. Thanks to this observation method, we can obtain a three-dimensional picture of how water vapor spreads around active comets. This information allows us to uncover details that remain hidden from traditional telescopes, providing a more complete and accurate understanding of comet dynamics and the processes occurring in their environment. For example, the Hubble Space Telescope provided high-resolution images that allow for quite precise determination of the size of the nucleus of Comet 3 IATL. It is estimated that its diameter could reach several kilometers, large enough to cause observable activity such as dust and gas ejections, yet small enough to be difficult to detect until it enters the influence zone of our solar system. Each new observation adds another piece to the complex puzzle, gradually revealing more details over time. However, solving this puzzle is complicated by the fact that modern instruments not only enable the detection of new objects but can also deceive automated data processing systems. These systems are designed to recognize familiar patterns and predictable behavior scenarios of astronomical objects moving along elliptical, or Keplerian, orbits around the Sun. When an object behaves differently, even slightly, these algorithms may either fail to notice deviations or, conversely, misinterpret them, masking genuine anomalies. Let us consider in more detail the problem of measuring changes in comet brightness. It is a misconception to think that a comet's brightness increases uniformly and predictably as it approaches the Sun. In reality, the process of brightness variation is a complex interplay of factors. It depends on the sublimation of various types of ice within the comet's nucleus, which occurs differently depending on its distance from the Sun. Additionally, the rotation of an irregularly shaped nucleus causes changes in the direction of solar illumination, leading to variations in observed brightness. Equally important are episodic dust and gas outbursts from active regions of the nucleus, which can significantly amplify or diminish the visible light flux, creating temporary spikes or dips in brightness. All these factors require careful attention and thorough analysis by specialists to distinguish natural variations from potential anomalies or signs of unusual processes. It should be noted that these very complexities make the interpretation of comet data an extremely challenging task. As an illustration, consider the green coloration observed in spectra obtained through spectroscopy, a classic example of the difficulty in determining the causes of a phenomenon. Various molecules can contribute to the spectral lines corresponding to the green color. One of the main culprits for green emission is diatomic carbon, which, when excited by solar radiation, emits in the green range. Cyanogen can also play a significant role, as it can produce similar spectral signatures when excited. However, without the use of high-resolution spectroscopy, which allows for precise identification of molecular composition, it is practically impossible to determine which specific molecule is responsible for the green hue. As a result, such assumptions remain more hypotheses than definitive diagnoses. Public perception of astronomical discoveries is often accompanied by excessive emotional coloring. When reports about unusual discoveries, often sensationalized, appear in the media, the level of uncertainty inherent in this information significantly increases. Preliminary reports may mention the presence of unexpected chemical compounds or unusual orbital characteristics, and interpretations are often formed long before the scientific community has had the chance to thoroughly analyze the data. Telescopes and astronomical instruments, by their very nature, do not possess desires or ambitions to make great discoveries. They do not seek fame or recognition. Their purpose is simply and strictly to perform their technical tasks, to record the flow of photons arriving from space and to accurately determine the positions of observed objects. This data is accumulated in a vast database that, over time, will become key to uncovering the secrets of our cosmic visitors. During this process of observation, an additional crucial aspect is added to the instruments, ensuring safety. That is why space probes, such as the 3 Atlas rockets and the SWR-2 satellite, follow specially designated trajectories that ensure their safe distancing from Earth and its immediate surroundings. These trajectories are calculated to minimize the risk of collision or other threats. For example, the 3 Atlas rockets will approach their targets at a distance of no less than 1/8 of an astronomical unit, approximately 270 million kilometers. Meanwhile, SWR-2 will reach its closest approach to Earth at a distance of 1/300th of an astronomical unit, just over 40 million kilometers. These distances pose no threat to our planet, rather, they open a unique opportunity for scientific research. It is precisely in these regions, under conditions significantly different from those in our solar system, that new, unknown objects and phenomena could have formed. However, at this very moment, science faces a certain challenge. As our satellites approach the Sun in 2025, both space visitors, Atlas and SWR-2, will begin to plunge deeper into bright solar illumination, which is clearly visible from the Earth's surface. During such periods, our terrestrial telescopes will lose the ability to continuously monitor them, as intense solar radiation interferes with obtaining clear and detailed data. In contrast, space observatories located in the vacuum of space are better equipped to handle this task. They continue observations, but their operational time is limited, requiring careful planning to determine which targets to study first, given the multitude of other scientific tasks and priorities they face. From these observations, an instrumental ensemble is formed, a picture composed of point data, spectral lines, orbital parameters, and brightness curves. Each such picture is a complex mosaic that allows astronomers to judge the nature and properties of the objects under study. However, interpreting this data is no easy task. They can reveal numerous possible scenarios, hypotheses, and developments, since images and spectra can be perceived differently. The question arises, what if our initial assumptions about them were incorrect? Or, more importantly, what if the tools we used to gather information have malfunctioned, and our expectations were mistaken? Telescopes continue patiently collecting light, capturing every photon and measuring the positions of objects with mechanical precision. They work tirelessly, observing the cosmos even as our visitors retreat deeper into the solar shadow. But with each step closer to the Sun, their whisper becomes quieter, and we begin to wonder, what secrets might be hidden in this growing silence? What unknown aspects of nature could be concealed in this fading visibility? Indeed, within this silence, within this diminishing light, lie many mysteries that require new approaches and deeper understanding. Part 3 is the language of metals, spoken in the language of atoms. It speaks just as the cosmic space does, in a language that can be deciphered if one understands its peculiarities. And the 3 atlases mentioned tell us a story written in an unexpected dialect. When a very powerful telescope directed its spectrographs at this interstellar visitor, it discovered something that forced astronomers to reconsider their expectations and recalculate their assumptions. In the center of the comet, in the near vacuum region around its nucleus, nickel vapor was detected, an unusual phenomenon, since at the same time, 3. Apparently, Atlas in school chemistry did not pay much attention, as his knowledge in this area seems insufficient. During observations conducted with the powerful Volga-Lussel telescope, as the comet approached its brightness peak on August 25, an astonishing phenomenon was observed. Spectroscopic lines indicating the presence of nickel appeared very brightly and stood out clearly against the overall spectrum background. In the same spectral range, attempts were made to find signs of iron. However, the result was quite remarkable. practically no traces of this element were detected. The upper limits of its concentration were so low that if iron had been present in typical cosmic amounts, it would have definitely appeared in the spectrum and been easily noticeable. This unusual chemical characteristic sparked numerous hypotheses and theories, each trying to explain how such a discrepancy could occur, attempting to reconcile the observation with modern physical laws. Perhaps, under interstellar conditions, organic compounds containing nickel are sufficiently stable at the low temperatures typical of interstellar space and only break down under the influence of solar heat, releasing nickel atoms into the surrounding environment. There is also a hypothesis that the processes of cosmic weathering occurring on the surface of this wandering ice for millions of years could have altered its chemistry in such a way that it significantly differs from the familiar samples we know, and these changes are not yet fully understood. In space, elements and molecules do not necessarily behave as humans expect. The universe imposes no restrictions on them except those dictated by physics. For example, Comet 2I, Borisov, which became the first interstellar visitor, also demonstrated its own chemical peculiarities, unlike those typical of comets formed in our solar system. In particular, its ratio of carbon monoxide to water was markedly different from the norm, indicating that it formed in colder, carbon monoxide-rich environments surrounding its parent star. However, observations from the James Webb Space Telescope elevate these chemical anomalies to a new level, revealing deeper and more intriguing aspects. Infrared measurements showed that carbon dioxide dominates the composition of this comet, while water vapor plays a noticeably smaller role, especially at the large distances where these observations were made. This distribution of substances suggests that inside the comet, there is likely a layered structure resembling an onion. The most volatile ices, such as carbon dioxide, are located on the outside, forming an outer layer, while water, which is less volatile, resides inside. In this context, the molecule cyanogen also appears, which is believed to be responsible for a significant part of the comet's green coloration. It adds another layer to this complex chemical portrait, as emission lines from CN, clearly visible in the spectra, indicate the dissociation of organic compounds under the influence of solar ultraviolet radiation. However, despite this, the intensities of various emission lines do not fully match the typical patterns observed in comets orbiting our Sun, suggesting subtle differences in their composition or structure. The green hue, which attracted particular attention and became a subject of public interest, still holds many mysteries. Although diatomic carbon is often considered the primary source of this green glow in comets, identifying the specific molecules responsible for this coloration remains elusive. It is possible that cyanogen, as well as excited states of carbon molecules, in one form or another, contribute to the green emission. Without the use of ultra-high-resolution spectroscopy, it is nearly impossible to definitively identify the culprits behind this vivid coloration. These chemical signatures transform into a complex narrative that challenges simple classification methods and requires deeper analysis. Let us imagine that atoms are letters, and molecules are words forming a unique language of celestial bodies. In this language, three atoms can be perceived as a dialect rich in carbon dioxide and metallic accents, which by their very nature do not quite conform to Earth's grammar and conventional chemical rules. Such a composition can be viewed as a special code that makes sense in the context of forming comets orbiting other stars, yet it appears sufficiently unusual and complex to attract the attention of scientists and researchers. Understanding the rate at which various gases form becomes another crucial key to decoding the nature of this cosmic object. As the comet approaches its stellar center, in this case, the Sun, a predictable increase in the speed at which it produces various molecules is observed. This phenomenon is expected and aligns with models for sublimating ices, processes in which frozen substances on the surface begin to turn directly into gas, bypassing the liquid phase. The mathematical foundations of this mechanism are well studied, allowing astronomers to make accurate predictions about the comet's future activity based on current observations. Nevertheless, even within these predictable scenarios, subtle anomalies and deviations are detected. The ratio of different molecular species in the comet's atmosphere does not always match models based on the properties and composition of comets known within our solar system. For example, brightness curves reflecting changes in illumination or activity show variations that may indicate heterogeneity in the nucleus's composition across its surface. Alternatively, they may point to discrete gas emission events, so-called gas outbursts, that could be triggered by subsurface processes hidden from our view and understood only hypothetically. These processes are likely related to the internal structure of the comet, about which only assumptions currently exist. The astronomy enthusiast community has played a significant role in studying these chemical mysteries. High-quality images taken by amateur observers from around the world allow for documenting the evolution of the comet's structure and changes in its tail, morphological features that develop as the comet approaches the star, over time as the three atoms near their perihelion. These observations provide vital temporal coverage that professional telescopes, limited by availability and priorities, often cannot fully supply. Thus, the contribution of amateur astronomers becomes invaluable, helping to form a more comprehensive picture of the ongoing processes. In the age of social media, some aspects of these chemical anomalies receive additional attention, sometimes turning into sensational news that outpaces scientific data. For example, the detection of nickel without iron has sparked controversy and various interpretations. Some researchers consider this evidence of artificial origin of the comet's metallic components, suggesting that these materials were specifically engineered rather than resulting from natural accumulation processes. Such a hypothesis requires extraordinary conclusions and goes beyond the confirmed spectroscopic data, leading to debates within the scientific community. The position of NASA remains unchanged. To date, all observations, despite some unusual characteristics, are consistent with the hypothesis of a natural origin for the comet. At the same time, scientists emphasize that such chemical features are quite expected for objects formed around other stars, in regions where temperature, pressure, and elemental composition can differ significantly from those typical of our solar system. Ultimately, the detected anomalies are more likely indicative of the richness and diversity of conditions under which these celestial bodies could have formed. The European Space Agency has also reached similar conclusions through its missions and numerous ground-based observations. Experts in astronomy and astrophysics agree that, recognizing the unique and unusual features observed in the interstellar object known as 3I Atlas, researchers studying interstellar objects note that the fundamental physics underlying cometary activity, the sublimation of ice processes that lead to the formation of gas and dust, provides a solid and logical basis for explaining most of the observed phenomena. This concept allows understanding what happens to such celestial bodies without resorting to exotic and hypothetical theories. However, science advances through the continuous and meticulous study of anomalies and unusual data, and Atlas, being one of the most chemically rich objects, represents a true field for research capable of keeping scientists engaged for many years. Among its spectrum are intriguing and rare elements, such as nickel emissions, dominance of carbon dioxide, characteristic cyanogen signatures, and green coloration, all of which become keys to understanding its nature and origin. Each new observation adds another crucial piece to the complex puzzle that could ultimately reveal many secrets about star system formation and the specific properties of this unusual visitor. As October 2025 approaches and simultaneously the moment when 3I Atlas will reach its closest approach to the Sun, the opportunities for conducting high-precision spectroscopic analyses will significantly diminish. The increasing distance from Earth and the reduction in solar illumination resulting from the comet's changing position in its orbit will make ground-based observations virtually impossible. At least, this is what one can assume. For several months, until the comet exits the influence zone of the Sun's gravity, obtaining precise data will be difficult, if not impossible at all. If we consider chemistry as a language, then studying the composition of Atlas is akin to reading a dialect of ice and metals that tell us about the conditions under which it formed, possibly hundreds of light years away from our planet. After all, our October sky remains an enigma. It may speak in a language understandable to us through encoded signatures or hint at something more complex and deliberately constructed. Atoms, as is well known, do not lie, they provide honest information, but sometimes this information is incomplete or hidden behind layers of interpretation. They do not tell us everything we would like to know, which is why we continue to question the meaning and significance of these cosmic messages. Let us move on to the next section. Imagine our solar system as a vast and intricate clockwork mechanism, where each component moves along a precisely defined trajectory. The planets, like accurate mechanical hands, trace predictable ellipses around the central star, the Sun. Smaller bodies, asteroids, comets, and interstellar visitors, follow their unique paths, intersecting and diverging like parts of a complex gravitational mosaic built according to the laws of mathematics and physics. In this context, we can imagine two uninvited guests arriving from completely different corners of space, following different orbits, but over several weeks approaching our Sun so that their paths cross. The probability of such an event, according to calculations, should be extremely low. Yet, in October 2025, we observe exactly this scenario gradually unfolding right above our heads, like in slow-motion film footage, showing a rare and astonishing dance of interstellar bodies. Turning to the object known as Atlas, which appeared in the sky from the constellation Ophiuchus in early July. Its appearance was a significant event, as it reached such brightness that automated space monitoring systems were able to detect it for the first time. This interstellar visitor moves along a hyperbolic orbit, which is a mathematical indication that the object is not gravitationally bound to our Sun. This object belongs to the class of long-period comets, which spend a significant part of their lives in the cold, sparsely populated outer regions of our solar system, closer to the so-called Oort cloud. There, in this distant and mysterious zone, comets are in a state of dormancy and only occasionally leave it, driven inward by gravitational forces that push them into the system. Exactly when these icy visitors begin to approach the Sun, their awakening occurs. Solar heat penetrating inward causes the ice to vaporize and creates bright tails, making them visible to observers on Earth. This object was discovered near the constellation Virgo as it just emerged from the Sun's glare, which had concealed it during its approach. Its geometry, meaning its position and orbit, reveals important clues to understanding the nature of such objects, how they originate, how they move, and what they contain inside. The detection of this comet was made possible thanks to modern methods and tools, since long-period comets generally remain hidden from our view until they come sufficiently close to the Sun for their brightness to become noticeable. Additionally, it should be considered that interstellar visitors like this object appear from arbitrary directions, complicating their detection. They can remain in regions of the sky that are too distant or too close to the Sun to be observed effectively for a long time. In the case of this cosmic wanderer, once it was finally observed, it had already passed Jupiter's orbit and was beginning to show the first signs of cometary activity, tails forming and brightness increasing, indicating its approach to the Sun. However, observers faced certain difficulties related to the Halley-type effect, a phenomenon where long-period comets suddenly become much brighter as they approach the Sun. This increase in brightness occurs precisely when the comet is still at a relatively small angular distance from our star, almost in twilight, making it difficult to see from Earth due to solar glare. Only when the comet's orbit takes it far enough away from the line of sunlight, beyond the bright solar disk, does it become visible in twilight or night sky layers. This explains why, in September 2025, observers were able to see the comet known as S1R2 for the first time. The timely alignment of the movement stages of these celestial objects creates a sequence of events that gives the impression as if someone deliberately planned this cosmic schedule. For example, comet Swan-R2 reached its perihelion, the closest point to the Sun, on September 12, passing at a distance of just under 5 astronomical units from our star. Meanwhile, the third object, Atlas, will make its closest approach to Mars, scheduled for October 3, passing at a distance of 30 million kilometers from the red planet. Around October 29 or 30, Atlas will reach its orbital perihelion, when it will be approximately 135 astronomical units from the Sun, about 3 times farther than Neptune's orbit. It is equally fascinating that the closest approach of the object SIR-2 to Earth is scheduled for October 21, when it will pass at a distance of 1 astronomical unit from our planet, essentially in very close proximity. Such a concentration of key events, the coincidence of their timing, over a 6-week period seems quite unusual and even astonishing. If these events occurred randomly, with a uniform distribution over time, the probability of such major orbital points and close approaches happening so near to each other would be extremely low. However, according to the laws of statistical mechanics, even the most unlikely events, given enough time and numerous opportunities, become practically inevitable. On the scale of the entire universe, which contains billions of stars, the object known as SWR2 presents a true cosmic spectacle, astonishing the imagination with its grandeur and scale. Its coma, that is, the bright, luminous cloud of gas and dust, extends across the sky for several degrees when observed through binoculars, creating the effect of looking at a glowing mist spreading across the entire celestial space. The tail of this celestial body, according to the testimony of experienced astronomers and amateurs, reaches lengths of up to 2 degrees, roughly equivalent to 2 full lunar disks visible to the naked eye. From a physical size perspective, such a scale amounts to millions of kilometers in length, and all these giant structures, despite their seemingly fragile appearance, are genuine cosmic masterpieces, reminiscent of spider webs stretched across interplanetary space. Their finest filaments, as delicate as spider silk, are so sparse and transparent that their density approaches the vacuum created in laboratory conditions. However, due to the vast volume of space they occupy, they become visible over enormous interplanetary distances. This visual poetry, evoking admiration and awe, unfolds against the backdrop of the Earth's constant seasonal changes. When autumn takes hold in the northern hemisphere, both of these celestial objects begin to slowly descend lower in the sky, approaching the western horizon after sunset. In this celestial spectacle, Swan Earth 2 holds a dominant position, acting as the main protagonist, attracting the attention of all who can look at the sky through a good binocular and have a clear view toward the constellation Virgo. For more detailed observations of this object, more serious equipment is required, such as an atlas, which helps determine its exact position and features. Its characteristic green hue, evident in photographs or images, makes it recognizable almost instantly after discovery. However, October brings both challenges and new opportunities to astronomy. It is precisely during this period that, thanks to their geometric positions and movements, conditions are created that both complicate the possibility of observations and open new prospects for study. As both objects approach their perihelia, that is, the closest points of their orbits to the Sun, they become immersed in its bright light more and more, as seen from Earth. As a result, at certain moments, ground-based telescopes will lose the ability to track these objects, especially during the most critical phases of their approach to the Sun for scientific research. This interval, often called the observational dead season, is not just an inconvenience or technical difficulty. It represents a significant gap in our knowledge that could be decisive for understanding the nature of these cosmic visitors. During the several weeks when ground-based instruments cannot see them, both objects will be subjected to the most intense solar heating. And it is precisely during this time that something unusual might seemingly occur, something previously hidden beyond the reach of our observational capabilities. If these objects possess any hidden characteristics or features, these invisible weeks could become the key moment for their detection and study. The retrograde motion of the 3 atlases adds another layer of complexity to understanding their orbital trajectories. Objects moving in the opposite direction relative to the main planets experience gravitational perturbations from various bodies and forces, which in turn influence their long-term paths. Although these perturbations are very small, they are measurable and help scientists in the future determine the mass and internal structure of the objects, provided they can track their paths accurately before and after perihelion passage. An example of this is the situation with Mars, which serves as our observational beacon during the October close approach of the 3 atlases. The orbital spacecraft, sent to the distant corners of our solar system, are equipped with modern spectrometers and high-precision visualization systems capable of revealing details and features of the objects that are invisible to ground-based telescopes, even when using the most advanced instruments. The geometry of observation from the surface of Mars during the flyby of these spacecraft creates very favorable conditions for obtaining the most informative data. In particular, this opens unique opportunities to study the structure of the comet and the dynamics of its tail, thereby complementing and expanding our knowledge gained from ground observations. Nevertheless, even with multiple viewpoints, advanced technology, and sophisticated instruments, the most critical questions remain unanswered, sparking much contemplation and debate among scientists. One of these problems is the coincidence in time, a mystery that continues to puzzle researchers who have dedicated many years to studying the statistical mechanics and dynamics of our solar system. In the vastness of space, where random encounters and collisions can occur over millions of years, the question arises: why are we observing the arrival of two such radically different objects at this particular moment, whose characteristics and trajectories seem almost to rhyme? Is this truly a coincidence, or is there a more complex, carefully orchestrated plan? Part 5. Theories gathered into a constellation. The human mind is a complex machine designed to find patterns and meanings in chaos. It evolved precisely to identify targets and determine directions amid the infinite flow of random events. When two celestial objects appear on the horizon, approaching our Sun within just a few weeks, exhibiting unusual properties and following nearly choreographed trajectories, our minds cannot help but construct various narratives. These stories often go beyond strict data, turning into attempts to explain mysterious close approaches and attractions, based more on imagination than scientific facts. They range from simple exotic hypotheses to outright fantastical scenarios, offering different lenses through which to interpret this unusual event that occurred on October 25. One such hypothesis suggests that the reconnaissance device named Fortress acts as a forward scout, a fast and maneuverable probe designed to study resources and the defense system of our solar system. In this scenario, the device codenamed Energy serves as the main base, a mobile platform, or a relay station providing communication and support for operations within the inner system. The timing of their arrival is not a random coincidence but rather part of a coordinated plan integrated into a larger mission that began many years or even decades ago in the cold, silent expanses between stars. From the perspective of maintenance and infrastructure support, it is assumed that both devices are part of an ancient automated monitoring system created by a civilization concerned with preserving and updating its technologies. These systems, apparently, operate on predictable cycles to monitor equipment status or periodically update software scattered throughout our local galactic neighborhood. Devices like 3 Atlas may carry new software modules or replacement components necessary for system modernization, while the Siren device provides power supply or other production capabilities that enable major repairs and maintenance. If we look at this hierarchy from a broader perspective, our solar system, within this hypothesis, is merely a single point along a regular patrol route, similar to the scheduled stops for maintenance within a system. This ancient patrol concept suggests that all these cosmic visitors are not random passers-by, but remnants of a long-standing monitoring network created millions of years ago by a civilization that feared the development of potentially dangerous forms of intelligence in our vicinity. Perhaps these devices are part of long-forgotten surveillance systems, which over the past century have been significantly expanded by humanity's radio wave horizons, and our signals sent into space have begun to penetrate beyond the atmosphere in vast quantities. As a result of this gradual expansion of the radio frequency bubble around the planet, our technological progress has created a powerful electromagnetic shell that continuously grows and becomes more complex. For decades, radio signals, television broadcasts, radar systems, and satellite communications have been spreading into space at the speed of light, forming an ever-increasing flow of electromagnetic traces around Earth that anyone with sufficiently sensitive instruments could detect. In this situation, there is a hypothesis that if someone or something in space were listening to this radiation, the response to our presence could be either reconnaissance devices monitoring our development or larger, more sophisticated platforms designed to assess the threat level posed by our technologies. Some researchers suggest that this might indeed be the case, that these are not accidental debris or natural phenomena, but deliberate objects reacting to our technological growth and evolution. Particularly provocative is the hypothesis that these objects are not merely random space artifacts but are what are called technological relics, possible traces of human civilization sent into the distant future when our descendants reach interstellar horizons and can send messages or artifacts back in time or along trajectories intended for arrival in specific past eras. Thus, these mysterious objects could be the result of complex technological processes or materials science beyond our current understanding, yet still leaving behind traces and characteristics that suggest a human origin. Their unusual chemistry, orbital parameters, and manufacturing features could indicate technologies that are currently inaccessible on Earth but remain recognizable within the context of human engineering. Historical and mythological interpretations of such mysterious signs often draw parallels with ancient legends about celestial messengers, comets, and unusual astronomical phenomena, which in culture were considered harbingers of great change. Throughout history, there have been legends on Earth about lights appearing in the sky, luminous phenomena that foretold the end of eras, the coming of new prophets, or even the apocalypse. These myths and legends served as ways to explain incomprehensible natural phenomena and to predict major historical events. Perhaps, modern cosmic artifacts such as the so-called Atlas and Swan Earth 2 are contemporary interpretations of these archetypal images, cosmic signs that divide one epoch of human history from the next. They may act as symbolic cosmic dividing lines, indicating transitions, changes, or development. When considering the dynamics of potential threats and defensive measures, the imagery of predator and protector takes on a darker tone. Suppose one of these objects, say Atlas, represents something dangerous, a weapon system, an espionage probe, or another form of threat. In that case, Swan Earth 2 could serve as a defensive system responding to the danger, or it might be the response of another spacefaring nation or civilization that sent this object to neutralize a potential threat before it reaches Earth. In the event of these two objects approaching each other, for example, on October 25, the situation could resemble scenes from a space battle or strategic confrontation, with Earth in the background and these objects in the foreground, acting as invisible yet potentially dangerous players on the cosmic stage. Such hypotheses and speculations are gaining popularity, as they challenge the fundamental limitations of traditional astronomy, which tends to assume that unusual phenomena must have natural explanations. This assumption has long served science, leading to the belief that all anomalies can be explained naturally. However, particular attention is drawn to unusual chemical signatures detected in the data, as well as the precise timing of the object's approach to the Sun and the pronounced coordination related to the parameters of SWR2, all of which serve as strong arguments supporting the hypothesis of their technological origin rather than a natural one. These observations emphasize that extraordinary claims require extraordinary evidence, and when such evidence appears, they demand careful attention and thorough analysis, as they could overturn our current understanding. Meanwhile, NASA and the European Space Agency maintain more conservative views, emphasizing that current observations and data, despite their unusual nature, still do not contradict natural explanations. Scientists from these organizations note that the number of interstellar objects recorded over the past 6 years remains extremely small, only 3 confirmed cases, which significantly complicates defining the boundaries between what is considered normal and what is anomalous for this rare category of cosmic visitors. This situation creates an internal conflict within the scientific community, reflecting deeper questions about methodological approaches in science and the nature of evidence itself. How unusual must an observation be for us to seriously consider hypotheses that challenge conventional views of the universe? And how can we balance scientific conservatism with the risk of missing truly revolutionary discoveries? Some aspects of these discussions have been heavily covered in the media, while others have remained in the shadows. Particularly active is the debate over the detection of nickel without iron, which has sparked a lively reaction on social media, where speculation about possible industrial processes or signs of manufacturing beyond the spectroscopic data confirmed by scientists is often circulated. At the same time, the main scientific mysteries related to the 3 interstellar objects continue to be at the forefront: their unusual composition of volatile substances, as well as the precise timing of their orbital coordination. especially parameters S1R2, all of which are based on more reliable and confirmed data. Meanwhile, psychological mechanisms of conspiracy thinking play an important role in how various theories are formed and spread. People tend to see hidden agents and schemes in random events, especially when it comes to phenomena that they believe could have significant consequences for humanity's future. In this context, the idea that cosmic visitors might not be random guests but deliberately sent beings or forces satisfies basic psychological needs for meaning and control in an apparently chaotic and unpredictable universe. Historical examples of such cases serve both as warnings and sources of inspiration. Every genuine revolution in astronomy, whether it be the discovery of the heliocentric system, black holes, or exoplanets, initially faced skepticism and doubt from established scientific institutions. However, history shows that unsubstantiated and unsupported claims usually fade over time, leaving lessons about how dangerous premature conclusions and speculation can be. An important opportunity to test these conflicting hypotheses will be the approach of Earth on October 25, 2025. At that very moment, scientists would have the opportunity to obtain new, more precise data and assess how realistic the theories are that suggest a technological origin for these celestial objects, comparing them with explanations based on natural processes. The story began its development when, at one of the most remote points on Earth, in the Atacama Desert in northern Chile, an astonishing event occurred. On July 1, 2025, a signal appeared that immediately drew the attention of automated sky observation systems. For a long time, this patch of the sky remained unchanged, its stars maintaining their constant positions, creating the familiar scene that astronomers have studied for ages. But this time, everything was different. One pixel on a sensitive detector, located on one of the modern telescopes of the Atlas Asteroid Terrestrial Impact Last Alert System, suddenly lit up unusually brightly. This instrument, designed to search for potentially hazardous asteroids, typically scans the sky, comparing current images with existing catalogs to identify any new, moving objects or those that suddenly increase in brightness. And it was precisely at this moment that its sensors detected something that did not fit the usual picture. A faint, barely visible speck that began to move slowly but steadily across the sky, leaving behind a trail of mystery. This object, dubbed the 3 Atlas, initially seemed unremarkable, just another space rock that accidentally entered the automatic system's field of view. However, the movement of this body, its trajectory, and dynamics began to raise more and more questions. Several hours after its discovery, as scientists started making more precise calculations, it became clear that this wanderer was moving along a hyperbolic trajectory, a path not associated with the gravitational pull of our Sun. In other words, the 3 Atlas was not an ordinary asteroid orbiting a star but rather resembled a visitor from interstellar space, arriving from the depths of the cosmos. This fact immediately attracted the attention of specialists, as such behavior is characteristic of objects coming from interstellar space, indicating that we are observing a rare phenomenon, possibly an interstellar traveler. If these cosmic visitors were simple comets or asteroids obeying familiar physical laws, their behavior as they approached the Sun should have conformed to well-known models of ice sublimation and dust emission. In that case, observing their activity, brightness, and changes during perihelion passage could fully confirm their nature and provide a clear understanding of what these objects are. However, if the 3 Atlas or Swan R2 turned out to be something more exotic, unusual, deviations from expected behavior should have manifested especially vividly during their approach to the Sun. And it is precisely at this moment, when they are in the most dangerous and simultaneously exciting phase of their passage, that their behavior should become most obvious and informative. But here arises a serious problem. All this scientific interest related to the objects passing through perihelion coincided with a solar flare, a powerful energy release that literally illuminates the entire solar sector and creates conditions that hinder observation of celestial bodies from Earth. Solar flares, being among the most powerful phenomena in our system, make it almost impossible or at least very difficult to obtain high-quality data on the behavior of objects at the most critical moment of their approach to the Sun. During periods of maximum solar activity, when its radiation reaches peak levels, both of these objects, the three atlases and Swan R2, are completely hidden from our ground-based telescopes, concealed behind a powerful solar flare or the solar disk. This creates a significant gap in our knowledge, forcing us to draw conclusions about the fate and condition of these bodies based only on what we can observe after they emerge from behind the Sun. At this moment, when the brightness and activity of the objects can change dramatically, we remain in the dark, which opens up space for assumptions, guesses, and speculation. Mathematical orbital mechanics divides all celestial bodies into two main categories based on the nature of their trajectories and their relation to our solar system. The first category includes objects that move along elliptical orbits, closed trajectories that bring them back to their starting point, that is, into our solar system. Bodies such as planets, large asteroids, and short-period comets follow these paths, completing a full circle around the Sun and returning to where they began. The second category consists of celestial bodies that pass by our Sun, moving along hyperbolic trajectories, meaning they make only a single pass and then disappear into the boundless cosmic emptiness forever. It is this category that includes our guest today, an interstellar object designated as 3 astronomical units, or 3 AU, which indicates that it primarily belongs to the rare objects confirmed to have passed through our system, and it is only the third interstellar visitor recorded by scientists in human history. The description of this object's orbital characteristics reveals the story of its journey, which began somewhere in the interstellar space beyond our system. The trajectory of this body is inclined at approximately 175 degrees relative to the plane of Earth's orbit, indicating its unusual direction of movement. This inclination indicates that it is approaching our solar system from below, that is, from the southern side relative to the plane of the ecliptic, and it is doing so in a retrograde manner, against the direction of planetary rotation. This fact suggests that the object likely formed in another star system, where conditions differed from those in ours, and after millions of years spent traveling through interstellar space, it has finally come into the path of our Sun. Its orbital movement and inclination resemble the traces of distant travelers crossing the vast interstellar expanse, leading to the hypothesis that this visitor originated from a distant star system where it formed under different physical conditions than ours. The story of discovering this interstellar object demonstrates how close we came to completely missing it. Interstellar bodies passing through our system usually approach from the most unexpected directions in space. They can be located in regions of the sky that are too distant and faint for our observational instruments, often passing by the Sun months or even years before we notice them. In this case, the object was detected only after it had already crossed beyond the outer boundaries of our system and had begun its final approach to perihelion, the point of closest approach to the Sun. Orbital data analysis shows that it was near our system possibly as early as the late 24th or early 25th century, slowly approaching our star and beginning to exhibit activity characteristic of comets. This delay in detection illustrates one of the main challenges in searching for interstellar objects. We can only notice them when they become sufficiently bright and when their position coincides with regions of the sky accessible to our instruments. According to forecasts, the closest approach of this interstellar traveler to the Sun is scheduled for around October 29 or 30, 2025. At that time, it will come within approximately 135 or 14 astronomical units, just inside the orbit of Mars. To understand the scale of this event, it is worth noting that this distance is slightly closer to the Sun than any previous interstellar body has approached. The trajectory of this object will pass near Mars on September 30, 2025, at a distance of about 30 million kilometers. Although this may seem like a very distant flyby from a human perspective, such a distance is quite accessible for modern space instruments and systems. The closest approach to our planet occurs when the space object is about 1/8 of an astronomical unit away, which is roughly 270 million kilometers. This distance is considered safe for Earth, as it eliminates the threat of collision from this celestial body. At the same time, it remains close enough for our most powerful telescopes to observe it during favorable periods when lighting conditions and its position allow for the most informative images. Estimates of the size of this object, provisionally designated as the 300th interstellar visitor, remain uncertain. However, it is assumed that its core is not very large, but rather modest in size. During observations conducted by the Hubble Space Telescope on July 21, 2025, it was possible to constrain the dimensions of this celestial body. Likely its diameter is only a few kilometers. Such sizes are sufficient to produce a bright coma and observable cometary light, yet significantly smaller than the impressive comets that have graced our sky in recent years, inspiring awe and wonder. The size estimate, however, is associated with considerable uncertainty, as observing such distant and faint objects is extremely challenging, especially given limited resolution and lighting conditions. The brightness we see is not due to the nucleus itself but results from sunlight scattered by dust and gases in the coma, an envelope of particles surrounding the core that glows brightly by reflecting solar rays. To accurately determine the true size of the object, complex modeling is required to understand how effectively the nucleus reflects sunlight and how much material it ejects into space through processes such as sublimation, melting, and evaporation of ice and other substances under solar energy. The organization of scientific research around the 300th interstellar visitor has become one of the most intensive observational campaigns ever conducted by humans for interstellar objects. As part of this effort, the Hubble Space Telescope provided high-resolution images that allowed tracking changes in the structure and brightness of the coma over time, as well as identifying features of its dynamics. Additionally, the James Webb Space Telescope, equipped with powerful infrared capabilities, was directed at the object in August to analyze its chemical composition. This enabled the detection of details inaccessible to ground-based observations and helped determine the materials making up this body. A very large ground-based telescope in Chile also contributed significantly by splitting the visitor's light into a spectrum, dividing it into component colors. This spectroscopic analysis helped identify specific molecules and atoms emitting light in the coma, as well as revealing unusual chemical signatures. Among these were particularly strong emission lines of nickel, along with the presence of iron and carbon dioxide, making this object especially interesting for science and capturing public attention. These observations allowed scientists to draw conclusions about the composition of the material constituting the body and about the processes occurring within its coma. Several other space telescopes continue to monitor this interstellar visitor as it approaches its anticipated first close encounter in October. However, with each passing day, the opportunities to obtain new and detailed data from Earth become increasingly limited. The growing distance and changing conditions of solar elongation, that is, the angle between the direction to the object and the sunlight, will eventually make ground-based observations impossible. As a result, we will largely depend on data collected by our interplanetary spacecraft, which are in orbits around Mars or other points within the solar system, during the brief periods when conditions allow observations. The organization and coordination of such international efforts demonstrate how modern astronomy has become a global enterprise. Telescopes located in Chile conduct observations almost nightly in the southern hemisphere, then transmit the collected data to Hawaii and the Canary Islands, as Earth's rotation shifts the view. Space observatories offer a unique opportunity to observe celestial objects continuously and independently of day-night cycles on Earth, as well as in any atmospheric conditions, which often hinder or entirely prevent ground-based research. These instruments, positioned in the vacuum of space, enable scientists to obtain high-quality, consistent data on a wide variety of cosmic phenomena, greatly expanding our capabilities to study the universe. However, among all achievements related to the use of space telescopes, one of the most exciting and unexpected discoveries was dubbed 3IATLS. This event turned out to be so astonishing that one might say we nearly overlooked it. The reason for this lies in the fact that the object we detected had very low luminosity, and its initial orientation and observation geometry were unfavorable. As a result, over several months, or perhaps even years, it quietly traversed our solar system, remaining almost unnoticed. This raises an important question: How many similar interstellar objects could have passed by us unseen because they were not bright enough or were positioned in such a way that their light never reached our telescopes? We must understand that the effectiveness of detecting interstellar objects depends on numerous factors, such as their size, composition, shape, and trajectory. Objects that do not develop large cometary tails may remain virtually invisible until they pass very close to the Sun, making them easier to detect. At the same time, objects moving from certain directions can be obscured by sunlight throughout their journey through the inner regions of the solar system, rendering them practically invisible to our observations. Statistical models based on data analysis suggest that for every interstellar object we detect, there are likely dozens or even hundreds passing by unnoticed. Therefore, 3IATLS is not only a unique scientific discovery but also a window into the possible existence of a far more numerous population of cosmic wanderers, who regularly cross our neighboring space region. This finding indicates that interstellar objects probably come to us much more easily and frequently than previously assumed, and our observations may still be hiding many of their secrets and peculiarities. As this mysterious object approaches perihelion, the closest point to the Sun, it continues its unwavering journey through the system, now observable by experienced astronomers equipped with simple yet effective telescopic instruments. Its greenish cometary tail has become a true hallmark of the autumn sky, serving as a reminder that our solar system is a kind of crossroads through which travelers from distant star systems pass. This bright, unusual object, like a cosmic guest, captures attention and delights astronomy enthusiasts, reminding us that the depths of space conceal many unexplored mysteries. Before it disappears into the Sun's rays and becomes unreachable to our eyes, it will have the opportunity to witness and participate in some of the most significant astronomical events. Of particular interest is the fact that Mars will be near its trajectory at this time, and planet that will take a front-row seat to observe all the most secret and extraordinary phenomena that might be hidden behind this comet. This will allow us to monitor its movement and characteristics from a new perspective, hoping to catch even the tiniest details and secrets. An important question arises: how advanced are our current tools, both on Mars and on Earth, to distinguish and study exotic and unusual objects within the very short time we have left to observe this cosmic wanderer? Part 7 of our discussion is dedicated to the unusual colors and mysterious chemistry manifested in this interstellar object. As is well known, the universe conveys its stories through various phenomena. In the field of studying cosmic phenomena, especially those associated with the mysterious green glow occurring in interstellar objects, scientists identify several main candidates capable of explaining this phenomenon. Among them, the most common are the participation of diatomic carbon molecules and cyanogenic radicals, both of which fluoresce brightly under the influence of sunlight. In specialized reviews dedicated to this unusual luminescence, published in scientific journals on life sciences and astrochemistry, leading hypotheses about the nature of the source of this bright green emission are examined in detail. Within the analysis, the importance was emphasized that, although diatomic carbon remains the most likely explanation based on numerous past observations of comets, the specific molecular species responsible for the coloration characteristic of the so-called three-atom spectral line have not yet been confirmed through high-resolution spectroscopy. This detail takes on particular significance, as different molecules tell different stories about the conditions in which these celestial objects formed and evolved. Cyanogen, a molecule composed of carbon and nitrogen atoms, is one of the most toxic and dangerous substances known to modern chemistry. However, it can glow with an ethereal, mesmerizing beauty when its particles are released into the vacuum of space. The presence of cyanogen in comet spectra serves as an important key to understanding ancient organic chemistry that took place in what is called the stellar nursery, where the three-atom spectral line was formed. The ratio of this radical to other carbon-containing molecules can provide valuable information about the temperatures, pressures, and chemical processes that occurred billions of years ago around a distant star, which served as the source for the formation of such objects. Despite all this complexity and recognized importance, the green glow is only the most visible aspect of a much richer and more complex chemical history that has been developing in space for billions of years. When a very powerful telescope located in Chile was pointed at the interstellar system known as the three-atom system, its spectrographs recorded molecular fingerprints that seriously challenged existing notions about the behavior of interstellar objects. Specifically, an unusual phenomenon was discovered: bright emission lines of nickel, which stood out against the spectrum, yet the expected traces of iron were absent. These elements typically coexist and are present in certain proportions, reflecting the nucleosynthesis processes in the stellar cores that formed them. According to established patterns, the prevalence and presence of nickel in space should correspond to the presence of iron, since both elements originate from the same nuclear reactions. However, observations obtained with highly sensitive instruments, such as spectrographs on telescopes at the Villar de la Tigua Observatory, during the comet's approach to Earth, showed a strong emission of nickel at wavelengths around 880 nanometers, corresponding to a bright green line. This line was clearly distinguished against the complex emission spectrum of the comet, creating a characteristic green glow. At the same time, searches for a similar iron emission at the same wavelengths yielded almost no results. Iron did not manifest itself at the expected levels, which was unusual and required explanation. The strict detection limits for iron obtained through observations turned out to be so low that, if iron were present in typical cosmic proportions, its traces should have been easily detectable. As a result, several hypotheses have emerged to explain this anomaly. One suggests that organic compounds containing nickel, which are stable in extremely cold interstellar conditions, could have decomposed under the influence of solar heat. Space weathering processes, occurring on the surfaces of celestial bodies over millions of years, can significantly alter their chemical composition. These long-term interactions with the cosmic environment may influence how various elements and compounds are incorporated into sublimating ices forming on the surfaces of objects. Consequently, the surface of the body acquires a unique chemical profile that differs from the initial conditions of its formation. This extended chemical profile was identified during numerous observational campaigns, allowing 3IT to be viewed as an object formed under conditions markedly different from those that existed during the formation of objects within our solar system. Such a difference indicates that its origin and evolution took place in a different stellar environment, with distinct temperature and chemical conditions. In particular, observations from the James Webb Space Telescope, using the NIRS-SPEC instrument, revealed that the comet's composition is primarily carbon dioxide. Water vapor plays an unexpectedly minor role during the early stages of the object's activity. This suggests that the comet formed in a colder, volatile-rich environment than that in which Earth and the other terrestrial planets originated. In various stellar systems, during the planet formation stages, temperature profiles can vary significantly, potentially leading to comets with unique chemical compositions that have no counterparts in our Oort cloud or Kuiper belt. According to an analysis conducted by the European Space Agency, the low water-to-carbon dioxide ratio observed at large heliocentric distances is a typical sign of early comet activation. During this phase, the most volatile ices sublimated first as the object approached the Sun. As the comet nears perihelion, the relative abundance of water vapor in the gas coma should increase because less volatile ices reach sublimation temperatures. The rate at which molecules such as water vapor, carbon dioxide, cyanogen, and others form provides additional insight into the nature of this cosmic visitor. As 3IT approaches the Sun, the formation rates of these substances predictably increase, decreasing with decreasing heliocentric distance. These irregular changes correspond to the expected patterns characteristic of the sublimation process of ices, providing compelling evidence that we are observing natural physical phenomena rather than artificial emissions. Nevertheless, within this model of predictable behavior, subtle anomalies are identified that pique researchers' interest. The ratio between the formation rates of different molecules does not fully align with models based on the chemical composition typical of comets in the solar system. Variations in the comet's brightness reveal patterns suggesting either heterogeneity in the surface composition of its nucleus or discrete gas emission events triggered by subsurface processes. These processes remain poorly understood, and their role in shaping the comet's chemical makeup requires further investigation. Amateur astronomy has played a significant role in documenting changes in the comet's chemical composition over time. High-quality images obtained by experienced observers worldwide provide time series of observations that surpass the capabilities of professional telescopes due to their limited observation time and competing priorities. Such observations offer valuable data on the dynamics of chemical changes occurring on the surface and in the atmosphere of the comet, contributing to a deeper understanding of the processes occurring in space over millions of years. These observations are aimed at tracking changes in the comet's characteristics, such as color, tail development, and overall brightness, and serve as a complement to more detailed spectroscopic studies conducted by major astronomical observatories around the world. In the modern era, social media has significantly heightened attention to certain aspects of these chemical mysteries, often transforming preliminary scientific results into sensational claims that frequently surpass the actual data in content and significance. This is especially evident in cases where nickel is observed without iron, which some researchers interpret as a possible sign of industrial activity or traces of manufacturing left in the comet's composition. Despite various hypotheses and natural explanations for this phenomenon, the official stance of space agencies like NASA emphasizes that current observations still support the hypothesis that this object is a natural comet visitor, albeit with some unusual but not unprecedented features. Scientists note that the chemical properties of such objects, formed in other stellar systems, can differ significantly from the familiar, as different stellar environments, characterized by variations in temperature, pressure, and elemental composition, may lead to the formation of unique chemical combinations not found in our solar system. An important aspect remains the distinction between exotic and unusual chemistry. The former refers to chemical properties that, although uncommon, can be explained by known physical processes, while the latter suggests a possible artificial origin, raising even more questions. In this case, particular attention is drawn to Atlas, which exhibits clearly exotic characteristics. However, whether these features cross the boundary into the realm of the unusual or remain within the realm of explainable phenomena continues to be a subject of active scientific debate and research. The historical context helps to view these chemical anomalies from a different perspective, providing valuable insight for their interpretation. For example, the previous interstellar visitor, Comet 2I, Oumuamua, also displayed its own chemical peculiarities that initially puzzled researchers. Specifically, the ratio of carbon monoxide to water in its composition differed significantly from similar measurements in comets belonging to the solar system. However, deeper analysis revealed that these differences could be adequately explained by formation in colder, more distant regions of its parent stellar system, supporting the possibility that such features can arise under certain conditions. Analyses conducted with very large telescopes, such as the VLT, include consideration of alternative chemical pathways capable of producing the observed nickel signals without resorting to hypotheses of extraterrestrial origin. One possible explanation is the formation of nickel carbonyl, a compound formed through a reaction between nickel particles in the interstellar medium and carbon monoxide at very low temperatures. This compound could potentially account for the dominance of nickel over iron in the comet's composition when heated by solar radiation. However, as the comet approaches perihelion, expected in October 2025, opportunities for detailed chemical investigations become significantly limited. The heat generated by solar heating activates the most interesting chemical processes but simultaneously complicates observations with ground-based telescopes, as the comet occupies increasingly complex viewing angles. This raises the question, could what we are observing now be not merely a natural awakening of chemical reactions under solar heat, but rather an activation of deeper protocols or systems embedded within its composition, indicating the possible presence of hidden mechanisms or intentions? The very molecular content of the comet, despite its apparent activity, does not reveal its true sources or formation mechanisms, which only adds more questions and underscores the need for further research. Their glow is an incredible phenomenon, akin to light waves governed by the laws of quantum mechanics that underpin all matter. These laws, with astonishing precision, determine the behavior of both natural objects and those created by the mind, although many of them remain a mystery to us, beyond our understanding. Part 8 of this story is dedicated to an event that can be called one of the most significant cosmic moments of the upcoming era. We are talking about the flyby of Mars, scheduled for October 3, 2025, an event that has been prepared for with excitement and anticipation spanning millions of years. On that day, 3 spacecraft, united into a system called ATS, will pass approximately 30 million kilometers from the red planet. Although this distance may seem enormous from a planetary science perspective, it still allows our robotic explorers to direct their instruments directly at this interstellar visitor to gather the most detailed and accurate data about its composition, structure, and behavior. In scientific terms, 30 million kilometers is roughly 5 times the distance between Earth and the Moon, or about 1/5 of an astronomical unit, which is the distance from Earth to the Sun. However, in the context of observing interstellar objects moving along hyperbolic trajectories at speeds of tens of kilometers per second, this distance offers a unique opportunity for detailed studies during the critical phase of the comet's approach to the Sun. The European Space Agency has already announced preliminary plans to coordinate efforts to effectively utilize several spacecraft orbiting Mars during this very short window for scientific observation. Among them is the ExoMars Trace Gas Orbiter, initially designed to study the atmosphere of the red planet, equipped with spectrometers capable of analyzing the chemical composition of the expanding comet 3IATLS. Also orbiting Mars for over 30 years is Mars Express, providing additional capabilities for imaging and spectroscopic analysis, greatly increasing our chances of understanding the nature of this cosmic visitor. Equally important is NASA's Martian Reconnaissance Satellite, equipped with the powerful high-rise camera, which, despite the significant distance, can provide unique details about the comet's structure, dust distribution, and the geometry of its tail. Although the comet will be too far away for detailed surface feature resolution, the sensitive instruments on high-rise can detect the finest structural elements invisible to ground-based telescopes operating through Earth's atmosphere. What is particularly important is that the geometry of observations during the flyby of Mars will provide us with advantages unavailable from ground-based platforms. The position of Mars relative to the Sun, comet, Earth line will create a unique opportunity to observe aspects of the comet's structure and its tail that are usually hidden from view from our planet's surface. The absence of atmospheric interference and atmospheric distortions, which are characteristic of ground observations, will allow for clearer images and more precise photometric data, significantly enhancing the quality of analysis. However, it should be noted that these plans are associated with serious challenges, since most Martian spacecraft were designed to study the planet itself rather than to observe distant objects in space. This complicates the task and requires high precision in planning and executing observational missions to maximize the potential for obtaining detailed data about the interstellar object during its critical approach to the Sun. The guidance systems, communication protocols, and data storage capacities used in this interplanetary project reflect the importance and complexity of the set priorities. All these components require accurate and coordinated efforts to ensure timely redirection of instruments toward targets located millions of kilometers from Earth, without losing focus on the main mission objectives. The scientific goals center around studying the comet approaching the Sun, especially concerning what are called the 3 aspects of active cometary terraforming, referred to as the 3 A's, 3 ATs. These areas remain insufficiently studied despite accumulated terrestrial research, so each observation from Mars offers unique opportunities to expand our knowledge. Detailed imaging of the comet allows for determining the distribution of dust particles in its coma by size. By analyzing how these particles scatter sunlight at different angles, scientists can better understand the structure and composition of dust particles, as well as the processes of their formation and interaction with the environment. Spectroscopic observations, in turn, can constrain assumptions about the ratios of various molecular species, especially during periods of active gas emission when the comet approaches the Sun. During this time, the intensity and composition of the gases released increase significantly, making spectroscopic data particularly valuable for understanding the chemical makeup and processes occurring within the coma. Another key objective for ground-based and orbital observations is the geometry and structure of the comet's ion tail. The interaction of the solar wind with the ionized gases surrounding the comet produces characteristic tail structures, which typically align with the magnetic field lines in that region of space. Thanks to the unique perspective provided by the spacecraft's position on Mars, additional information about the dynamics of this tail, its velocity, and structure can be obtained, observations that are impossible from Earth. These features of the ion tail allow for more precise determination of gas emission rates and local space environment parameters, as well as insights into the interaction between the solar wind and cometary gases. The timing associated with the approach to Mars adds a sense of urgency to these plans. In late October, the 3I Atlas orbiter will experience the greatest solar heating during its closest approach to perihelion, the point in its orbit nearest to the Sun. This period is expected to mark the peak activity of gas emission from the comet, likely reaching its maximum at this time. The flyby of Mars at this moment offers a unique opportunity to conduct studies that could shed light on the physical processes occurring in comets, potentially not repeated for decades or even centuries. However, even the most advanced and sophisticated instruments aboard the Martian orbiter face limitations. The 30 million kilometer distance transforms the observed object, the comet, into more than just a point source, making it impossible to resolve details of its nucleus or obtain detailed maps of the comet's morphology with current orbital systems. Additionally, delays in radio signal transmission between Earth and Mars significantly complicate real-time observation planning. Depending on the relative positions of the planets, delays can range from 4 to 24 minutes, meaning that commands and observation parameters must be prepared in advance and uploaded to the spacecraft's memory. The ability to make quick adjustments and modify observation parameters in response to rapidly changing comet activity or sudden behavioral shifts is severely limited, requiring meticulous and predictive planning. An important factor is the dust environment on the surface of Mars. While large-scale global dust storms occur relatively infrequently, regional and local dust phenomena happen much more often and can substantially reduce observation quality. Dust can interfere with imaging and sensor sensitivity, complicating the acquisition of accurate data. The schedule for returning collected data during this space event adds another layer of complexity and uncertainty to the existing observational challenges. Typically, Mars rovers transmitting scientific data to Earth do so during strictly scheduled communication windows, which unfortunately do not always align perfectly with the brief periods when Mars is close to Earth. These communication windows are often limited in time, and their coincidence with the moments of closest approach, when the object is at its nearest point to Earth, does not always occur as promptly as desired. As a result, some of the most interesting and significant observations may not reach our planet until well after the closest approach, sometimes days or even weeks later. This delay significantly restricts our ability not only to coordinate subsequent observations quickly but also to disseminate preliminary results in a timely manner among the global community of astronomers and space researchers. Nevertheless, despite these challenges, the approach to Mars presents a unique opportunity for scientists to study the interstellar visitor in its most active phase. During this brief window, Earth-based telescopes will be able to track the object while it is still visible from Earth, as shortly after closest approach, solar illumination will hinder observations, making them virtually impossible. As the object plunges into sunlight, our ground-based instruments will lose the ability to observe it, rendering upcoming observations from Earth's surface almost the last chance to obtain a clear image or important parameters of this interstellar body. Such observations could become invaluable sources of data, enabling scientists to test and compare various theoretical models attempting to explain the nature of the interstellar visitor. Comets like this one, which experience intense heating as they approach the Sun, typically exhibit predictable patterns of dust and gas ejection. These patterns manifest in changes in the brightness of their comae and the morphological structure of their tails, allowing researchers to infer details about the internal organization and composition of the body. Any significant deviations from these expected patterns could indicate the presence of more exotic or unusual features characteristic of this interstellar object, opening new horizons for scientific investigation and theoretical speculation. However, it is important to maintain realistic expectations and understand that even the most advanced observation and analysis methods do not guarantee a complete picture or the uncovering of all secrets of this cosmic visitor. It should be remembered that the approach to Mars does not imply any direct contact or even a very close pass. The object will remain at a distance exceeding millions of kilometers throughout the entire approach phase. No surface samples, detailed internal data, or other physical characteristics that could be obtained through direct contact will be accessible. All observations will be based solely on remote sensing methods, which undoubtedly impose certain limitations, but at the same time serve as an important demonstration of the potential to develop and test new technologies and techniques for future interstellar object research. In practice, the methods developed and validated during the approach of this interstellar body to Mars could form the basis for designing observation strategies in future missions. These strategies will enable more effective coordination of international efforts to study such rare cosmic travelers, expanding our knowledge of interstellar objects and their nature. In planning these activities, possible unforeseen situations are necessarily taken into account: technical failures, communication difficulties, or unfavorable geometric conditions that could restrict or entirely prevent the collection of necessary data during the approach. To minimize risks, backup scenarios are prepared, including the use of ground-based telescopes and other observation tools capable of providing additional sources of information. However, even these face limitations, such as increased sunlight, atmospheric interference, and other factors, especially during the most intense phase of approach. The schedule of this event compresses the most scientifically valuable observation window into just a few hours or at most a few days around the closest approach. If Mars had the ability to listen to the electromagnetic spectrum during those critical hours when space is filled with chaos and mysteries, it could potentially intercept countless stories hidden within the static of interstellar waves. These stories include the sounds of distant stellar flares, the rustling of cosmic particles, and the quiet whispers of potential messages sent by unknown civilizations, or simply random sparks of energy penetrating through space. Instruments installed on the red planet will listen with the patience characteristic of machines and with the genuine curiosity of their creators. People who believe that answers to the deepest mysteries of the universe can be found in the light of a starry wanderer. They hope to decode any messages embedded in these radio waves and light impulses, as if signals indicating the existence of other life forms or unknown processes occurring beyond our current understanding. But first, whether a space observer or an adventurer, the guest must complete their encounter with the fourth planet of our solar system, carrying with them all the secrets it holds, and must pass by the vigilant eyes of Martian guardians, those few robots and sensors guarding its borders, in order to reach their final destination. There, behind the blinding glare of our sun, awaits a new chapter full of mysteries and discoveries. Part 9. Swan Earth 2, The New Giant. While one astronaut, known as 3AJ Atlas, attracted widespread attention as if an exotic guest from interstellar depths, another space traveler quietly but confidently prepared for his star demonstration. Comet C25R2, more widely known as Swan R2 after its discovery in data from the Solar and Heliophysical Observatory, emerged from the dark depths of our own solar system to become one of the brightest and most spectacular sights observed from Earth's surface in recent years. The story of this discovery begins with the patient and persistent work of amateur astronomer Vladimir Bezruchny, who spent hours scrutinizing images obtained by the SWAN instrument and searching for signs of a new comet hidden in the sunlight. His perseverance paid off on September 11, 2025, when he noticed an unusual increase in brightness in the data, which was soon confirmed. A new, previously unknown comet was emerging, approaching its perihelion, the closest point of its orbital path around the Sun. The SWAN Solar Wind Anomalies instrument, located aboard the SOHO spacecraft, was initially designed to study the interaction of solar wind with the interplanetary medium, but it became an equally important tool in comet detection. Thanks to a hydrogen atom distribution map created during the dissociation of water molecules under the influence of solar ultraviolet radiation, this instrument can detect comet activity that often remains unnoticed by ground-based telescopes. This is especially true for objects located too close to the Sun, where observations from Earth are fraught with difficulties and risks associated with solar radiation. The appearance of comet Swan R2, which emerged from solar conjunction, illustrates one of the main challenges in discovering comets: their long and complex trajectories, often passing at very small angular distances from our star. The Holostack effect, named after the Austrian astronomer who first described it, explains why many impressive and bright comets suddenly appear in our sky already fully formed and active. This effect shows that most comets moving along long-period orbits spend months approaching the Sun from different sides, often at small angles, making them difficult to detect. By mid-September 2025, the team of astronomers could confidently observe that the comet, tentatively called Swan R2, was beginning to display its bright and noticeable form in the dark sky. At a time when most objects in the night sky remain invisible without optical aid, it reached approximately the 6th magnitude, the threshold at which, even under good observing conditions, an object can be seen with the naked eye. However, unlike many other comets that typically reach their peak brightness and then gradually fade, Swan R2 continued to grow brighter and brighter. This was because it was leaving the solar encounter, approaching its closest distance to Earth, and thus becoming increasingly visible to observers. On the day marked by astronomers as September 16, a photograph was published in the Astronomy World's Photo of the Day section, capturing this new cometary object. The images clearly showed the rapidly increasing brightness of the comet, as well as its impressive tail, which had already reached a significant length by that time. Thanks to these images, Swan R2 became one of the most discussed topics among amateur astrophotographers worldwide. Its convenient position near the bright star Spica, located in the constellation Virgo, served as an excellent reference point for those trying to spot it in the twilight sky. Experienced observers began actively recording and sharing their impressions. Their reports noted that the comet's tail extended approximately 2 degrees in the sky. This is about 4 times the diameter of the full moon, making it quite noticeable even to the naked eye. Although these measurements were more approximate, subject to subjective visual perception and differences in digital image processing methods, they still provided an idea of the scale of this cosmic phenomenon. The tail was estimated to stretch millions of kilometers in physical length, creating a truly spectacular visual effect. The orbital parameters of Swan R2 tell their own story, opening the way to understanding its origin and trajectory. Unlike the comet with a tentative name, 3, which was moving along a hyperbolic interstellar trajectory, this object followed a rather elongated elliptical orbit. It carried it from the distant icy depths beyond Neptune's orbit, at a distance of about half an astronomical unit, that is, slightly more than 30 million kilometers, from the Sun's center. Such a path implies long decades or even centuries of travel, during which the comet remained in a frozen state and showed no activity. Only after solar heat reached its surface did its active phase begin, transforming it into a bright and dynamic cosmic phenomenon that attracted the attention of all observers. A particularly significant date in the history of this journey is when Swan R2 reached its perihelion, the point closest to the Sun. This occurred on September 12, 2025, when the distance to the center of our star shrank to approximately 0.5 astronomical units, roughly half the distance between Earth and the Sun. This close approach caused the comet to experience intense heating of its icy surfaces. As a result of this process, sublimation of the ice occurred, releasing dust and gases that created the characteristic appearance of the comet and its tail, which points away from the Sun. The most favorable time to observe Swan R will be on October 21st of next year, when the comet will pass at its closest distance, exactly 27 thousandths of an astronomical unit, which is approximately 40 million kilometers. During this period, observers can expect the comet to appear brightest and most clearly visible. The continuous increase in the comet's brightness indicates that in the coming months it could reach magnitudes of 8 or 9, making it one of the brightest celestial objects observable in 2025. This noticeable intensification of its glow has generated particular interest among astronomers and enthusiasts. as it offers the opportunity to see this rare visitor from the depths of space with the naked eye, and to record its appearance in observational logs throughout its approach. Especially favorable viewing conditions are provided by the southern hemisphere, since from this region the comet passes through the evening sky, coming closest to Earth. While residents of southern latitudes will be able to observe it high above the horizon, northern observers still have a chance to see the comet, albeit at a lower position relative to the western horizon after sunset. The comet's position in space relative to the ecliptic plane and its movement concerning Earth create constantly changing geometric conditions for observation, affecting its brightness and visibility at different times. International amateur astronomy groups from various countries have intensified their efforts to document every stage of SWR2's development, creating extensive real-time observation databases. These data not only complement professional research results but also allow tracking the dynamics of its characteristic changes, which is especially important given the short observational arc since the object's discovery and the lack of long-term information. Experienced photographers and astronomers use high-tech equipment to capture high-resolution images that reveal the finest details of the tail's structure. Among these are potential signs of element disconnection, when interactions with the magnetic field temporarily detach parts of the ion tail from the main body. Such phenomena provide a unique opportunity to study the processes occurring within the comet and help understand how its components interact with solar wind and magnetic fields. However, despite advances, significant uncertainties still remain regarding the orbital characteristics of SWR2. The reason for this is the relatively short observation period that has existed since the object was discovered. Comets, as is well known, are influenced by non-gravitational forces resulting from gas emission, a process in which particles and gases released from the nucleus create reactive forces that subtly alter the body's trajectory. That is why accurately predicting the comet's future behavior is difficult until more data becomes available. To refine the orbital parameters and determine the future fate of this celestial traveler, specialists at the Small Planet Center are actively collecting and analyzing new astrometric data received from various observatories around the world. These measurements are of great importance. Ultimately, they will decide the comet's destiny, whether it will return along a closed elliptical orbit, bringing it back into the inner regions of the solar system, or whether gravitational perturbations caused by passing through a strong gravitational field will push it forever beyond the system, turning it into an interstellar object. Currently, estimates indicate that the threat to Earth is extremely low. The current approach distance, approximately 2/7 of an astronomical unit, provides a significant safety margin, allowing specialists to conduct observations with high precision and remain unconcerned about potential threats. This distance offers unique opportunities for detailed studies aimed at understanding the composition, structure, and behavior of the comet, as well as obtaining valuable scientific data that will help elucidate the processes involved in the formation and evolution of such objects. To ensure safety and improve forecast accuracy, continuous monitoring of the comet's trajectory is maintained, with particular attention to any unexpected changes that may arise due to nucleus activity or interactions with the solar environment. In a rapidly evolving situation with sudden changes in such objects, specialists employ all available means for timely response, which is especially important for acquiring up-to-date information. Vasili's interest in the appearance of the comet has elicited a broad response and has become the subject of lively discussions and educational programs. Despite the fact that a significant portion of the telescope observation time is dedicated to studying three objects associated with an asteroid named Atlas, or three Atlases, particular attention is drawn to its exotic interstellar source, Swanner II. This object holds special value for astronomers because it opens unique opportunities for studying the composition, characteristics, and behavior of objects beyond our solar system. The coincidence in time of Swanner II's appearance and the passage of the three Atlases through the inner regions of the solar system creates an exceptionally rare and important situation for conducting comparative studies. These two objects, drastically different in origin and nature, one being an interstellar body, and the other part of the Oort cloud located in the distant reaches of our solar system, are nonetheless subjected to similar physical processes, provided they are in conditions of solar heating. This circumstance offers scientists an extraordinary opportunity to study how the environment of formation influences the behavior of comets and similar bodies. If the three Atlas objects can be considered as scouts, performing the role of explorers of our cosmic neighborhood, then Swanner 2 appears as a herald, like a messenger of considerable size, announcing upcoming events or phenomena far more extensive than they initially seem. This entire phenomenon seems particularly fateful. The universe rarely provides such favorable conditions for comparative studies, making October 2025 a special month capable of fundamentally changing our understanding of what occurs in the spaces between stars and within their systems. In this context, there arises an opportunity to rethink and expand existing theories about the nature of interstellar objects and their interactions with our system. Moving on to technical aspects and hypotheses, it is worth focusing on engines, protective shields, and orbital trajectories, areas where the line between the exotic and the engineering often becomes blurred. In the realm of speculative astronomy, where observations can give rise to the most unusual hypotheses, extraordinary phenomena serve as a source of inspiration for developing new theories about possible aspects of the universe's structure. A universe filled with intelligence and unknown forms of life that may exist beyond our current understanding. Images like Tree Atlas and Swan Earth 2, despite potentially being explained by natural processes, simultaneously provoke reflections on more provocative hypotheses. These hypotheses might concern, for example, the artificial origin of such objects or their controlled movement. Within such considerations, even thoughts about the physical principles related to directed motion, controlled energy release, and other aspects can serve as mental experiments, exercises for the mind where we explore scenarios beyond conventional notions. Let us first consider the question of the presumed drive. Natural comets, as is well known, follow trajectories entirely determined by gravitational laws. Their paths in space are dictated by the inverse square law of gravitational attraction, as well as initial conditions formed in distant star systems or during their ejection from them. Any artificial device capable of influencing the movement of such bodies would have to manifest itself through noticeable deviations from these predicted orbits. Such deviations can manifest as constant acceleration vectors, changes in orientation, or course adjustments that violate the classical principles of ballistic motion accepted in astronomy. For example, a directed plasma engine operating by ejecting ionized gases at high speeds would produce characteristic signatures. These signatures would appear both in the trajectory of the object and in its electromagnetic spectrum. The exhaust plumes of such an engine, illuminated at specific long wavelengths determined by the composition and temperature of the expelled material, would make the object detectable. The gas emissions observed by our most sensitive instruments fully coincide with natural sublimation processes caused by solar heating. This fact is beyond doubt, as these processes are well known and confirmed by numerous observations. However, the fact that the precise timing of these gas emissions, as well as their arrival near Mars and Earth, occurs within a very narrow time window and coincides with the moments when S1 Air 2 probes approach our planet raises serious questions that require deeper analysis. Such coincidence seems so precise that it challenges purely statistical expectations, especially when considered from the perspective of theoretical possibilities. It can be hypothesized that if this temporal similarity is not due to chance but rather to coordinated processes, then this indicates the existence of systems capable of controlling such events with incredible precision. This, in turn, suggests that there are propulsion systems operating with such finesse and synchronization that our current observational methods cannot detect or record them. Electromagnetic shielding is another area where natural phenomena can mask or imitate artificial processes. For example, comets, as natural objects, develop plasma envelopes around themselves resulting from interactions between solar wind and the ionized gases they eject into space. These interactions create complex magnetic structures capable of deflecting charged particles, forming characteristic anti-solar ion tails, and generating a magnetic field-like effect around the comet. In the case of artificial objects, an active electromagnetic system could appear very similar to these natural plasma interactions. The difference would lie only in the degree of control and directionality of this field, which could be tuned to exert specific influences on the surrounding charged particles. A key aspect in distinguishing such systems would be the detection of magnetic field configurations that serve no apparent natural function, for example, not related to signal transmission, energy collection, or radiation shielding, but instead used to control and deflect the solar wind according to a predetermined program. Modern observations confirm that ion tails of comets behave as expected during natural interactions between the solar wind and the comet. Spectroscopic studies conducted by the James Webb Space Telescope and ground-based spectrographs do not reveal any anomalous electromagnetic signatures. Neither coherent radio emissions nor signs of controlled electromagnetic field formation beyond those naturally arising from solar activity and comet interactions have been detected. Orbital mechanics, which plan patrol routes, also serve as an important tool for identifying artificial objects. In particular, the presence of repeat visitation schemes or systematic patrols allows us to distinguish artificial trajectories from random interstellar objects, which typically move along unpredictable and chaotic paths. Long-period comets originating from our Oort cloud can be disguised as single phenomena, even if they move along closed elliptical orbits, since their orbital periods often exceed human observational history. Therefore, only through repeated appearances and predictable intervals between them, coordinated arrivals of multiple objects, or noticeable modifications to their trajectories can we conclude the artificial origin. These signs act as strategic indicators used to detect and analyze such objects, rather than merely random cosmic phenomena. Regarding interstellar visitors, over the past approximately 6 years, starting with the first recorded object in 2020, then Oumuamua, DWA, Borisov, and finally, Tri, Atlas, and others, none have shown signs of systematic distribution or coordinated activity that could suggest artificial origin. The hypothesis proposed by scientist Avalob suggests an interesting and rather unusual mental experiment, which questions the possibility that our own electromagnetic signals leaking into space could trigger automatic reactions in monitoring systems scattered throughout our local galactic neighborhood. The idea is that a sudden and impressive radiation emanating from Earth could be perceived not as a natural cosmic signal, but as something that causes automatic responses in systems designed to detect and analyze potential interstellar messages or threats. Such a hypothetical scenario would explain the existence of a temporal correlation between our technological development and the appearance of unusual cosmic objects or phenomena, which seemingly arrived in our region immediately after humanity reached a certain level of radio-technological progress. This hypothetical mechanism suggests that our signals could have triggered a chain reaction, activating automatic observation systems for neighboring star systems or galactic structures, ultimately leading to the emergence of those mysterious objects or phenomena that intrigue scientists. However, despite all these assumptions, space agencies such as NASA and the European Space Agency currently assert that existing observations and collected data are fully consistent with natural processes, even if they possess unusual and sometimes seemingly exotic characteristics. These organizations emphasize that, in order to make truly sensational and extraordinary claims, one must have irrefutable and convincing evidence confirming an artificial or extraterrestrial origin of the observed phenomena. At present, analyzing spectroscopic signatures and the dynamics of orbital trajectories, scientists find that all observed features, whether chemical components, mechanical movements, or physical behaviors, fit entirely within what can be expected from natural cosmic processes. In particular, spectra obtained from both three-dimensional astronomical telescopes and the Swan Air System show signs corresponding to the range of cometary phenomena, only at its extreme or more rare end. That is, the observed chemical signatures, such as the presence of nickel without iron, can be interpreted as manifestations of natural processes rather than evidence of artificial origin. This explanation is based on the understanding that chemical traces found in cosmic objects can arise from both natural processes and technological activity. Specifically, industrial processes, especially those related to extraction, processing, or disposal of various elements, are capable of selectively concentrating certain isotopes or chemical compounds. These concentrations can leave characteristic traces in waste emissions or volcanic and meteoritic ejecta. In the case of cosmic objects like comets, Such chemical signatures may appear as a result of natural processes associated with their evolution, aging, or interaction with cosmic radiation. The analysis, conducted with advanced instruments such as the Very Large Telescope, VLT, involves careful consideration of all possible pathways for the formation of such chemical elements and compounds. It includes a discussion of natural mechanisms such as nickel chemistry, carbonyls, effects of cosmic aging, and processes of selective sublimation. That is, the gradual transition of substances from solid to gaseous state under the influence of temperature and radiation, which contributes to the appearance of similar chemical traces without invoking hypotheses of technological origin. An important area for differentiating natural and artificial processes is the change in the color of objects and behaviors associated with their inclusions or structure. Typically, comets exhibit nonlinear brightness increase curves related to the fact that various volatile substances reach their sublimation points at different distances from the Sun. These brightness jumps create the impression of discrete activations, which may seem to be evidence of some sort of process. For a long time, leading radio institutions and major radio observatories, such as Arecibo and others, conducted systematic and carefully organized searches for possible signs of artificial origin emanating from various cosmic objects or visitors. These facilities attempted to detect any signals that could indicate the existence of intelligent civilizations or technological structures capable of sending electromagnetic messages into space. However, despite all efforts and modern technical means, no coherent transmissions or structured electromagnetic emissions have been recorded in any observations that would clearly indicate active use of electronics or technological systems characteristic of artificial objects. No signs have been found in such studies that could suggest technological activity or automated information transmission systems from the observed objects. Additionally, radar observations carried out by several different groups and international teams confirmed the absence of noticeable reflective characteristics or radar signals originating from supposed visitors or other cosmic structures. These results are especially significant given the enormous distances that radar systems must traverse to detect and record such signals. In practice, even the most powerful planetary radars face substantial difficulties in detecting such objects, as interstellar distances are extremely vast, and signals are weakened and dispersed over enormous expanses of space, greatly complicating their detection and interpretation. The lack of strong radar signatures supports the hypothesis that such objects most likely have surfaces composed of low-density materials such as ice and dust, which are common in space, especially in regions where comets and asteroids are found. These surfaces reflect radio waves much less effectively compared to metallic or artificially constructed structures, which are presumed to have more prominent radar activity. Therefore, the absence of noticeable radar signals supports the hypothesis that these bodies, their surfaces, and structures are of natural origin. Infrared observations serve as another crucial tool for differentiating between artificial and natural origins of celestial objects. Spacecraft and artificial constructs typically exhibit thermal signatures associated with internal heat generated by life support systems, thermal regulation mechanisms, or the use of new, exotic materials with distinctive thermal properties. These thermal signatures differ from those emitted by natural objects such as ice or dust heated by sunlight. In particular, observations made with instruments like the 3A Atlas and SWR-2 revealed infrared emission profiles that entirely matched models of solar heating typical for ice and dust surfaces, with no signs of additional internal heat or unusual heat sources. This suggests that these objects are most likely natural formations rather than artificial structures created by intelligent beings. The energy budgets proposed under various technological scenarios also cast doubt on the possibility of these objects being of artificial origin. Interstellar travel requires enormous energy expenditures, whether for acceleration, maintaining life support, or ensuring communication across gravitational distances. Objects capable of such large-scale movements and technologies would likely exhibit signs of advanced energy systems and infrastructure, which, unfortunately, have not been detected in our observations so far. Modern instruments have found no evidence of powerful energy plants, unusual energy sources, or technologies that could be associated with highly developed extraterrestrial civilizations. The international scientific community has well-established protocols and procedures designed to respond to the detection of truly anomalous and unique phenomena that could indicate the presence of extraterrestrial technologies or contacts. If several independent observatories were to simultaneously record such phenomena, the gap between what we can directly observe and what could theoretically exist in the vast expanse of space creates numerous scenarios that remain beyond our current capabilities to confirm or refute. This is especially evident in cases involving rare and unusual objects whose existence and behavior raise many questions. Modern tools and observation methods, although significantly advanced over the past decades, still do not allow us to encompass the entire spectrum of possible phenomena and entities that may lie beyond our observational capabilities. As a result, some scenarios remain hypothetical, and their verification is either impossible or extremely difficult, creating space for numerous interpretations and assumptions. The human mind, by its nature, tends to seek patterns and meanings in the surrounding world. In an effort to understand natural phenomena, we often resort to explanations based on technological or other hypothetical premises. An explanation that seems logical and appealing often reflects a deeper human desire to find a sense of purpose and order amid the chaos of the cosmos. When new information about unusual cosmic objects emerges today, for example, about extraterrestrial visitors or mysterious celestial bodies, our minds begin constructing narrative models, attempting to connect them into a logical sequence. These models frequently interpret such phenomena as potentially artificial, since the presence of unusual characteristics or sudden approaches to our solar system arouses interest and sparks speculation about possible intelligent activity. Statistical analysis of the frequency of interstellar objects shows that even if there appears to be a recent increase in unusual cosmic bodies, this is most likely attributable to the effect of selective observation. In other words, with the development of technology and the refinement of detection methods, we have become more willing to notice objects that previously went unnoticed. In the past, when our observation tools were less sensitive, such objects could pass by without attracting attention. Now, thanks to improved technology, we record and analyze many more. As a result, it seems that the number of such unusual objects is increasing, but in reality, this may be an illusion caused by our heightened awareness and capabilities. An example can be given of 3 interstellar objects discovered since the mid-2000s. The first is the object named Oumuamua, the second, Borisov, and the third, Atlas. All of them exhibited characteristics that initially puzzled researchers and raised many questions. For instance, their unusual shape, brightness, or trajectory appeared to contradict conventional models. However, after detailed and multifaceted analysis, it was established that each of these phenomena has a quite natural explanation. As a result, their peculiarities were attributed to natural origins, and even the most astonishing properties ultimately turned out to be the result of natural processes or random interactions, unrelated to any intervention by intelligent beings. This fact sets an important precedent and prompts reflection on the nature of unusual cosmic objects in general. It demonstrates that possessing extraordinary characteristics does not necessarily indicate an artificial origin. Sometimes, such properties may seem strange or even astonishing because we have not yet fully understood the complexity and diversity of processes occurring in space. After all, nature is full of mysteries, and what appears to us as incredible or supernatural may, in fact, have a completely natural explanation that simply requires deeper investigation and analysis. Modern computer modeling of interstellar object trajectories confirms that our solar system has been regularly encountering natural visitors, so-called cosmic wanderers, for millions of years. According to models, their arrival frequency should roughly match current observations, considering estimates of the population density of such objects in our local galactic neighborhood. In other words, if we make reasonable assumptions about the number and velocity of such bodies ejected from other star systems, the recent visitation rates fit well within the expected range. Earth-based telescopes at certain times will lose the ability to observe 2 objects approaching the Sun. This will occur precisely during their closest approach to our star. This period, when observational instruments on Earth cannot detect what is happening, will create a so-called observational blind spot during the most critical phase for science. This gap in our knowledge means that the most compelling, and possibly the only, evidence of the technological origin of these objects could appear precisely when we are physically unable to observe them. Such an observational gap raises concerns, because it is during this time that a discovery could occur, fundamentally changing our understanding of the nature of interstellar objects. Observatories located on Mars, during the third passage of a hypothetical interstellar comet or another object designated as the third astronomical transport system, this October, represent our best chance to maintain observation during this crucial period. However, it is important to remember that existing Martian orbiters, despite their technological sophistication, were primarily designed for studying planets and their atmospheres, not for detecting exotic phenomena that might originate from interstellar travelers or artificial devices moving across interstellar distances. If, along the path of these cosmic wanderers, genuine machines, artificial structures, were suddenly encountered, their detection would require specialized observation and analysis methods that go far beyond current astronomical practices. Modern technologies and methods designed for detecting natural celestial bodies may prove insufficient for recognizing signs of artificial origin, especially if such devices possess the ability to mask themselves or appear as ordinary natural objects. The difference between a sufficiently advanced technology and a natural object capable of looking very natural can be so subtle that current scientific models and differentiation criteria might fail or produce a false sense of naturalness. In this context, an important question arises, not whether we have already found evidence of extraterrestrial visitors or artificial machines, but rather, would we be able to correctly identify them if such objects truly existed in forms and manifestations that surpass our current understanding of what technology capable of interstellar travel and functioning for millions of years should look like. For example, if such a machine could disguise itself as a comet or another natural object, what would we actually see through our telescopes? Perhaps everything we observe are objects that evoke our confusion and challenge our existing understanding, remaining sufficiently natural at first glance to avoid requiring extraordinary evidence, and thus not prompting extraordinary claims. As is well known, the universe is adept at keeping its secrets very carefully, revealing them only to observers who are sufficiently experienced to ask the right questions and patient enough to accept that some answers may lie beyond our current technology and knowledge. This is one of its mysteries. Some secrets remain hidden until the opportunity arises to understand their true significance. Let us turn to the overarching question: what could possibly connect these two cosmic visitors? In the theater of space, coincidences suddenly turn into carefully planned conspiracies, and time into a complex choreography where the human mind attempts to find patterns in the chaos of the universe around us, in its vast and mysterious expanse. Two objects, appearing just weeks apart, demonstrate similar characteristics and follow trajectories that ultimately intersect near our Sun within the same narrow time window. All this begins to look less like coincidence and more like part of a larger, meticulously coordinated plan, if we allow our imagination to fill in the gaps left by the lack of data. Within this hypothetical model, which can be called speculative or even fantastical, a large cosmic object, often referred to as a comet, appears not merely as an icy body subject to natural cosmic processes. Instead, its massive structure and constantly growing tail can be interpreted as a complex and carefully designed logistical platform managed by artificial systems. This entire structure conceals behind its seemingly unstable exterior the presence of meticulously tuned mechanisms responsible for resource management, communication, and navigation. Such a concept suggests that the comet is not merely a natural formation but a multi-layered system, in which each element is part of a larger technological chain. Additionally, smaller and more maneuverable spacecraft, which can be conditionally called Third Automatic Transport Systems, or Third ATS, serve as scouts. These devices gather valuable information about the characteristics of our solar system, its planets, atmospheres, and other features, then transmit the collected data to larger and more complex platforms. In this configuration, a warehouse, a scout, and a larger base station, one can see a logical chain that explains some of the mysterious aspects of the observed behavior of these objects. For example, the precise timing of their movements, trajectories, and bearings may indicate deliberate navigation, aligned with preset coordinates. These coordinates could point to locations such as the main station or communication node, intended for receiving transmitted data or for system maintenance. Regarding the chemical signatures observed as unusual gas emissions or plasma traces, their interpretation within this model might differ from simple natural phenomena. Perhaps these signals are controlled discharges, carried out to transfer fuel, manage the atmosphere, or dispose of byproducts of technological systems. These systems likely operate under extreme temperatures and pressures, causing the release of gases and plasma traces perceived as anomalous or unusual. In an alternative version, both objects, the large comet-like body and the smaller reconnaissance crafts, may not be natural entities but the result of ancient technologies, possibly placed within a global monitoring system. These objects could have been created or captured by an ancient interstellar network scattered across the local galactic region. Thus, instead of specially designed spacecraft, these bodies could serve as natural carriers of technological infrastructure. Their surfaces or internal spaces might have been modified or adapted for use as platforms for automated systems, which activate under certain conditions. For example, upon detecting electromagnetic emissions indicative of advanced technological civilizations or when other conditions related to energy or information needs are met. Such a scenario would explain why these objects exhibit characteristics that can hardly be considered purely natural and are more indicative of a technological origin. Any civilization with sufficient technological advancement to create interstellar monitoring networks would likely prefer to keep their activities secret. Camouflage and imitation are essential tools in such a tactic. They allow avoiding provoking defensive reactions from encountered species or civilizations, which might perceive these objects as threats. Transforming natural bodies such as asteroids and comets into covert platforms is almost an ideal way to protect against potential threats or unwanted attention. The shell of these bodies, their surface, and internal structures could serve as cover for artificial systems disguised as ordinary cosmic debris, creating the illusion of natural objects while hiding highly sophisticated technological complexes inside. In this hypothetical model, the Sun itself not only functions as a gravitational focal point or a light source. It becomes a powerful energy resource powering these hidden systems. Solar radiation is an inexhaustible energy source. The creation of the Sun's gravitational well forms natural points of concentration where various types of information from distant sensors and observation stations can be collected, processed, and then transmitted further to even more remote monitoring systems located deep in space. Within this context, our joint approach to a specific point in time, scheduled for October 25, might be perceived as a routine operation of data collection, analysis, and transmission, part of the normal rhythm of cosmic activity. However, from a deeper analytical perspective and considering the dynamics inherent to hunters and gatherers, this coincidence in timing takes on a more sinister and mysterious tone. If we consider a model where the three components, designated as ATLS, operate as a predatory system, their main task is to detect and eliminate emerging threats. The Swan Air Platform 2 could instead serve more as a resource extraction and processing platform. This system is intended to handle any materials or information gathered by the hunter, whether energy resources, space debris, or other forms of matter. The difference between a nimble scout operating on the periphery and a powerful processor designed for data processing and analysis reflects their strictly specialized roles within a larger and more complex cosmic organization, which views our solar system either as a potential opportunity for development or as a danger that needs neutralization. The images emerging within this hypothetical model depict scenes where a small scout, a courier, spirals closer to a meeting point or observation platform, while large installations equipped with collectors and processing systems are deployed for rapid response and ready to receive any materials or information delivered by the scout. The apparent comet-like activity we observe may conceal far more targeted operations, such as energy collection, matter transformation, or the construction of temporary infrastructure necessary to support long-term missions conducted near our planet. All these scenarios exist solely in the realm of imagination, not confirmed by direct observations. However, they are so convincing and compelling that they can capture human attention. This occurs because they create a structured narrative that helps organize and make sense of phenomena which, in reality, seem random, chaotic, and disconnected. The human mind has a deep tendency to see in coincidences something more than mere chance. It prefers to seek explanations that imply intent, purpose, or even hidden motives. Even when such explanations require stepping beyond known data and making extraordinary assumptions, this drive to find meaning often leads us down fascinating, albeit hypothetical, interpretive paths. Within this struggle between randomness and perceived choreography of events lies a deeper philosophical question about the nature of intelligence, its manifestations in the universe, and our ability to recognize it when encountering extraordinary forms of existence. If we assume that advanced civilizations regularly employ technologies that imitate natural processes, for example, processes that appear natural to us but are actually artificially created, then an important question arises. How can we distinguish genuine natural phenomena from sufficiently complex and well-designed artificial systems? This problem becomes especially relevant in light of events occurring by October, as they create a real temporal structure around which various hypotheses and hypothetical scenarios can be built. For instance, the flight of the third Atlas past Mars on October 3rd, followed by the overheating event of the third ATS on October 29th, and finally the closest approach of Earth to the Sun on October 21st. These events form a sequence in space and time that can be perceived either as a random coincidence or as a carefully orchestrated cosmic choreography organized by someone or something. Historical mythological parallels from human culture provide rich templates. Throughout the history of every human civilization, legends and traditions have preserved stories about mysterious celestial visitors who appeared on the horizon at special moments in time, heralding changes in the fate of nations and states. These legends describe vivid light phenomena in the sky, fires that seem to ignite with enormous burning spheres or flare up with dazzling stripes, and they are called fires in the sky. According to tradition, these extraordinary spectacles served as harbingers of significant events: the establishment of new empires, the fall of dynasties, the emergence of new knowledge, or shifts in power. Perhaps modern phenomena, such as mysterious objects designated by provisional names like Three-Eye Atlas and Swan Earth 2, represent a contemporary interpretation of ancient archetypes and mythological models that have lived in the subconscious of humanity for centuries. A recurring motif throughout our research and reflections is the image of a comet or a bright luminous fortress in the sky, as well as a mysterious signal or message sent from space, about which we have even less awareness. This motif gains particular significance if we consider it as a response or reaction to a sent message. In this context, the appearance of two linked objects, one symbolizing the message and the other representing the response, becomes a crucial milestone. Their convergence could signify the completion of a long and complex communication exchange that began when our radio emissions first penetrated the cosmic space several decades ago, during the era of the first radio signals sent by humanity into the universe. At this stage of our investigation, when we are approaching a deeper understanding and analysis, it is important to emphasize that we are moving from purely hypothetical assumptions to a certain level of awareness. We set aside purely observational data and facts to boldly venture into the realm of more risky and highly intriguing hypotheses and theories. Our reasoning is grounded in scientific facts, timelines related to the October period, chemical signatures recorded in space, orbital mechanics. All these elements continue to support natural explanations for the observed phenomena. Even when ideas about extraterrestrial contacts and civilizations inspire us and give rise to more exotic hypotheses, they do not exclude rational and logical scientific interpretations. The question of a possible joint mission or cooperation between these cosmic visitors implies the presence of coordination and interaction, which, in essence, has not yet been confirmed by scientific data. At the same time, situations involving coincidences and random overlaps are often explained by simpler and more terrestrial reasons. It is quite possible that the purpose of these phenomena is nothing more than a natural process, rather than a pre-planned program or project. The mind analyzing such mysteries most often seeks explanations within the framework of known laws of physics and astronomy, as these frameworks provide a sufficient level of understanding and allow us to explain most observed phenomena. These assumptions reflect not only our psychological needs to find meaning and patterns but also embody genuine scientific enigmas related to the behavior of interstellar objects and possible extraterrestrial visitors. At the same time, it is impossible to completely rule out the possibility that some technological achievements, hidden behind opaque distances or complexity, may appear as manifestations of natural processes, including those intentionally created by their designers or as a result of engineering solutions based on fundamental physical laws. If such technological systems do indeed exist, they require detection and analysis methods that surpass our current scientific capabilities and demand new approaches and tools. A key aspect in confirming the hypothesis of coordination among visitors will be their behavior during exposure to solar heat and radiation, especially during periods when both objects pass through the most intense phases of heating. It is precisely at these moments, when their characteristics may change or manifest in unusual ways, that signs of interaction or coordination might be detected. The possibility of discovering new evidence capable of challenging our most basic assumptions about what is moving and hidden in the dark spaces between stars is becoming increasingly relevant and exciting. If we assume that such cosmic objects have a common mission, then the question arises: what specific task requires the simultaneous use of both a sharp instrument and a powerful factory? Perhaps the answer can be found at the very heart of our star, the Sun, in those mysterious weeks when its fiery flames might produce the very events capable of overturning our understanding of cosmic processes. During these moments, two enigmatic cosmic visitors could take their final steps before the eyes of humanity, after which they might disappear forever, leaving behind only whispers in the archives of memory and subtle speculations among scientists. Section 12. The Hypothesis of Relay, Space Data Dump. In the realm of speculative astronomy, where the boundaries between imagination and strict physics are blurred, very few scenarios evoke such a sense of purposefulness and deep mission as the idea of transmitting information across cosmic spaces. According to this hypothesis, three objects, conditionally labeled as Atlas, serve as messengers delivering data, while their closest satellite to Earth, SWR-2, acts as a center for processing and relaying information. All of this occurs near our Sun, where the most complex data exchange, prepared over years and often decades, is completed. Imagine these three atlases as interstellar couriers, carrying compressed archives of observations accumulated over a long journey through the local galaxy. Their modest size and agile trajectory suggest a priority on speed and maneuverability rather than large storage capacity. However, even the smallest of them can hold an enormous amount of data if modern encoding and storage technologies are employed. These unusual chemical signatures we observe in space may not be remnants of natural processes at all, but rather controlled data recordings, physical carriers imprinted on the object as it approaches the meeting point. The SWR-2, emerging from the farthest corners of our solar system, serves as a supplement to the data processing and retransmission system designed to ensure reliable information transfer. Its impressive scale and dynamically evolving tail may conceal complex data arrays and communication systems specifically engineered to operate in the extreme conditions characteristic of stellar environments. The apparent cometary activity of these objects could serve as a cover for more sophisticated mechanisms, such as directed energy beams, plasma systems, or unusual communication technologies that operate through interactions with solar wind and magnetic fields. The Sun itself becomes a key third participant in this hypothetical data transmission operation. Our star, the most powerful energy source within hundreds of astronomical units, is capable of powering complex systems that would be impossible with portable power sources alone. But its role extends beyond merely being an energy provider. The Sun creates a unique physical environment where the interplay of gravitational effects, magnetic fields, and plasma dynamics could reveal new principles of communication beyond our current understanding. Gravitational lensing, for example, could potentially serve as a mechanism for establishing connections over vast distances, utilizing a large-scale infrastructure encompassing an entire star. Thus, the Sun transforms into more than just a luminous body. It becomes part of a system enabling information exchange between civilizations or objects beyond our comprehension. Einstein's general theory of relativity predicts astonishing and highly practical phenomena related to the curvature of spacetime by gravity. Specifically, it indicates that massive objects like stars can distort the paths of light and other electromagnetic radiation, creating natural focusing systems, or in other words, gravitational lenses. These natural lenses function as unique, extraordinarily powerful telescopes capable of concentrating radiation from distant, and even very distant, cosmic sources. As a result, for an advanced civilization with sufficient technological power, such gravitational foci could become natural points where relay stations are placed. These stations, installed at the gravitational focus points, would enable the creation of interstellar communication networks spanning the entire galaxy. Stars in such systems would serve as natural signal amplifiers, significantly increasing the efficiency of information transmission over vast distances. Moving on to more exotic aspects, it is worth noting that the plasma environment surrounding our Sun and other stars creates a wide range of physical possibilities that could open new horizons for civilization. Within the solar system, the solar wind, a stream of charged particles constantly carried along planetary orbits, contributes to the formation of complex electric currents and magnetic structures. These magnetic fields and currents, with advanced technology, could be used for manipulation and information transfer. Imagine systems where information is recorded directly into the plasma flow, encoded in the configurations of magnetic lines and structures passing through interplanetary and interstellar space. Visually, such processes might resemble large-scale natural phenomena, concealing technological operations that, at first glance, are indistinguishable from Earth's meteorological or magnetic storms. Some systems could appear as collection surfaces, artificially disguised as natural gas or magnetic clouds. These surfaces efficiently harvest solar radiation, enabling photosynthesis and other biological processes to seem primitive compared to technological systems that utilize solar energy for data processing and transmission. Data storage units made from crystalline matrices are capable of withstanding extreme conditions of the interstellar environment, such as radiation, high temperatures, and cosmic winds. Within these systems, terabytes of compressed data are exchanged between various nodes operating at the edge of matter and energy. The concept of using sunlight as an energy source for processing and transmitting large volumes of information reflects the need for powerful energy resources in interstellar communication. Transmitting signals across galactic distances requires colossal amounts of energy, so much that even star systems with abundant reserves face certain limitations. It is highly probable that specific time windows, such as October 20, 2025, for example, will become optimal moments for conducting such operations. On this day, due to the coincidence of factors such as solar activity, planetary alignments, and the positioning of receiving stations, the most favorable conditions are created for data transmission with maximum efficiency. The cloud of radio waves surrounding the Earth plays a key role here. This radio wave shell is the result of human activity, caused by the continuous emission of electromagnetic signals into space since the early 1920s. Over this time, our planet has emitted numerous signals into space, forming an expanding sphere similar to an artificial bubble extending approximately 100 light-years in all directions. This radiation bubble serves as a kind of indicator of human technological development, evidence of the formation of complex communication and information exchange systems on Earth. For monitoring systems capable of detecting and analyzing these signals, it represents an important reference point. If we consider that automated monitoring systems detected our first radio transmissions several decades ago, it should be noted that full reception and processing of such signals require considerable time. In particular, communication systems in remote regions would need to establish reliable channels capable of transmitting data over vast distances. Additionally, navigation in interstellar space involves complex orientation and course correction systems, and coordination with local relay infrastructure also takes a significant amount of time and resources. As a result, the current wave of so-called visitors, or objects, detected in space most likely represents a reaction to our own electromagnetic emissions, a response signal initiated by our radio transmission, which propagates into interstellar space and could be perceived by someone or something. However, reality often turns out to be much more complex and unpredictable than our hypotheses and scenarios suggest. To date, scientists and experts in astronomy and space research have found no signs of narrowband radio emissions that could originate from other truly functioning interstellar communication systems. If such signals existed, they would likely have characteristic features typical of artificial sources: narrow bandwidth, stable frequency, and a specific structure. No anomalous accelerations have been recorded that could indicate controlled or artificially corrected movements of these objects. Their chemical composition and physical behavior remain within the realm of natural phenomena, comparable to cometary bodies, albeit at the extreme and unusual end of such natural processes. Overall, all observed parameters of both objects, both the first and the second, do not exceed the bounds of natural cosmic phenomena, which confirms the opinion of the majority of specialists. The official position of NASA and other leading space agencies continues to be that current observations are best explained by natural causes rather than artificial origins of the objects. They emphasize that in order to confirm the hypothesis of extraterrestrial origin, convincing and irrefutable evidence is necessary, not just unusual characteristics or coincidences. Although both discovered objects possess some features that evoke interest, they do not exhibit signatures that definitively indicate the presence of engineering or technological traces beyond what could result from natural processes in space. If we assume that these objects are not merely natural bodies, then the question arises: who sent them? This question generates numerous hypothetical scenarios, each of which says more about human psychology than about space visitors. Perhaps these objects are messages from our future, sent back in time through complex technologies capable of manipulating space-time dimensions. There is a hypothesis that they could be the result of time travel or the use of technologies allowing movement into the past and future. Others suggest that these objects are representatives of parallel evolutionary branches that achieved interstellar capabilities millions of years ago and are now observing the development of life and intelligence in our local galactic space. Alternative scenarios depict images in which both objects are part of ancient automated systems created by civilizations that reached interstellar technological capabilities long before Earth existed. According to some theories, these civilizations may have disappeared or vanished entirely, leaving behind only their technological infrastructures, monitoring and communication networks. In such a case, we are not talking about intelligent beings but about mechanisms functioning as technological fossils, systems that would continue to operate even after their creators had disappeared. They may have transformed or become extinct millions of years ago and now continue to perform their functions automatically, without any external support or guidance. However, testing the hypothesis of interstellar relay channels and communication systems is a complex task. The infrastructural requirements for creating truly genuine interstellar communication systems surpass the complexity and scale of all existing industrial capabilities of civilizations that have been imagined so far. These difficulties stem from the fact that modern technologies, based on our current understanding of physical laws, are unable to provide stable and efficient interactions over interstellar distances. However, it is important to emphasize that these limitations apply exclusively to the arsenal of methods we now consider advanced and achievable. In reality, civilizations that have mastered interstellar travel and communication may operate based on principles that render our notions of energy, information transfer, and interaction as outdated as signal smoke seems to a user of 20th-century fiber optic networks. That is, what currently appears impossible to us within the framework of 20th-century physical laws could become commonplace and quite familiar for species possessing knowledge and technologies of the 21st century, just as today we find the use of the internet or smartphones ordinary. In this context, the retransmission hypothesis offers an intriguing concept that not only satisfies narrative needs but also allows us to turn random cosmic encounters into purposeful events of information exchange and communication. It suggests that humanity has somehow broken free from a vicious cycle of technological development that made us unworthy of attention from intelligent beings observing the galaxy. These beings may be monitoring the development of civilizations in search of signs of life and intelligence, and upon noticing our achievements, they decide either to interact with us or at least to observe us. Thus, the retransmission hypothesis implies that we are not alone in the universe and are not going unnoticed, that our development is not purely accidental, but is observed and possibly even guided by forces operating on scales beyond our current understanding of space and time. These forces could be so vast and complex that we can only speculate about their existence and purpose. However, for this hypothesis to become more convincing, it requires us to accept extraordinary claims based on evidence that, despite their unusual nature, persistently appear as ordinary. It also demands the search for rational explanations where observed phenomena seem mysterious, and the coordination of efforts where, despite the lack of complete proof, simpler and more logical explanations seem preferable. The crucial point is that if the retransmission hypothesis is correct, almost every significant event related to our potential contact with extraterrestrial civilizations should manifest during specific periods, such as when our cosmic neighbors approach the Sun, and their data transmission peaks due to increased energy availability and the most favorable windows for communication. However, the key problem lies in the difficulty of distinguishing natural activity of comets or other celestial objects from signals that may originate from information processing systems operating under extreme heat and radiation conditions. If data transmission occurs at the moment when our telescopes are in a state of blindness, hidden behind the bright glare of our own star, that is, during the most critical phase of a potential operation, we may end up with nothing but more precise measurements of ice sublimation and dust dynamics. At the same time, there is also a possibility that we will encounter compelling evidence suggesting that our solar system is not merely a starting point but a transit hub for communication networks spanning the entire galaxy. In such a case, the hypothesis of retransmission transforms our Sun from a simple star into a kind of cosmic postal station, and our October visitors, from random wanderers undertaking routes originating in distant star systems, whose names we do not yet know, into active participants in a grand interstellar network. It remains unclear whether the 13th part of our narrative opens before us an exciting and sometimes incredible picture of a scenario for collecting cosmic resources, where fuel, fields, and lights play key roles. Imagine that our Sun, so familiar and dearly loved, unanswerable to questions, is actually not just a bright luminary illuminating our world. It is a colossal energy source created billions of years ago through nuclear fusion, which has been ongoing for about 4.5 billion years. Over these epochs, it has converted more than 4 million tons of matter into energy every second, and this power seems so fundamental to all living and non-living things on the planet that we rarely think about its vast scale and astonishing capabilities. However, deep in our reflections, we should ask ourselves, what if our Sun is not just a star serving as a beacon and a source of life for Earth? What if it performs the function of some cosmic refueling station, a giant reservoir of energy and rare resources that civilizations gather and utilize according to a strictly defined schedule, calculated over millennia, not human centuries or decades? Imagine that the components involved in this system are not accidental but operate according to pre-established laws and rhythms, located in space like automated mechanisms. For example, 3 satellites similar to Atlas and 2 SW-Air-type devices. All of them serve as elements of a complex resource collection system arriving at our Sun not by chance but according to long-established patterns. These devices operate based on specially developed algorithms, allowing them to perform their missions accurately and efficiently. The smaller of the two functions as a geodesist and coordinator, constantly measuring the characteristics of solar radiation, plasma flow parameters, and conditions near the star to optimize the energy extraction process. It acts as a regulator and balancer for the entire system, ensuring maximum efficiency and safety in accomplishing the task. Meanwhile, the larger installation deploys collection systems in orbit, disguised as natural phenomena such as comet activity, concealing artificial mechanisms behind the appearance of natural processes. These systems carefully divert energy and materials emanating from the outer layers of the solar atmosphere, utilizing advanced technologies that combine engineering ingenuity and physics, allowing resource extraction without damaging the star's environment or attracting undue attention. This scenario suggests that harvesting processes are somewhat covert, almost magical actions that we perceive as natural cosmic phenomena. For example, the magnificent tail of comet Swan Earth 2, which we are accustomed to seeing as a bright and beautiful spectacle in the sky, may not be merely a random natural event but could serve a hidden function. It might conceal artificial magnetic funnels designed to direct solar wind streams into specially prepared processing systems. With closer inspection, it becomes clear that what we consider passive and natural movements of ion tails are actually the result of carefully controlled exhaust jets emanating from large-scale solar engines. These thrusters, operating on scales far exceeding any human industrial enterprise, enable precise control of particle flows, guiding them into designated resource collection and processing systems. All of this is carried out with exceptional precision to avoid attracting attention and to prevent our increasingly advanced instruments and observation systems from detecting these processes. It can be assumed that such civilizations have long mastered the art of harmoniously working with natural forces rather than opposing them. They develop and utilize technologies that amplify and direct natural processes, integrating them into their technological infrastructure rather than replacing them entirely. It is evident that what we perceive as the ordinary behavior of comets, their tails and movements, may, in fact, be the result of meticulously optimized ion acceleration mechanisms specifically designed for efficient resource extraction. This approach is not a coincidence or merely a random interaction. The extreme conditions necessary for the operation of such unique interdimensional wormhole networks can naturally occur only in special astronomical environments, for example, in stellar coronas, the thin outer shells of stars where magnetic field intensities reach values thousands of times greater than Earth's magnetic field at the surface of our planet. In these regions, the gravitational wells formed by the star's powerful gravity approach the boundaries where effects described by general relativity begin to play a crucial role and significantly influence the behavior of space and time. It is precisely under such conditions, where magnetic fields and gravitational forces reach extreme levels, that the physical parameters required to sustain wormhole systems can arise, making these locations unique in the context of searching for and utilizing hypothetical technologies. In October of this year, the starry visitors of our solar system, potential interstellar objects or celestial bodies, may find themselves in a position that allows them to exploit these unique physical conditions. During this brief period, when the geometry of magnetic and gravitational fields is most favorable for the realization of exotic physics, conditions are formed that are ideally suited for conducting complex operations related to the integration and operation of such technologies. Consequently, this period offers the most effective opportunities for manipulation and research in harnessing extreme space conditions to achieve our goals. The process of extracting energy and resources from such environments may follow specific cycles linked to the sun's rotation and magnetic activity. Over the solar month, approximately 27 days, our star completes a full rotation, during which natural oscillations in the orientation of its magnetic field and changes in the density of solar plasma occur. These cycles create rhythms comparable to waves of light and shadow, and it is these oscillations that our instruments can detect as natural variations in brightness and activity. Thus, solar activity not only plays a vital role in shaping cosmic conditions but also creates predictable rhythms that can be used to synchronize and optimize resource collection processes. The aforementioned 27-day cycle of the Sun's rotation establishes natural rhythms for the orientation of its magnetic field and plasma distribution, which in turn creates stable conditions for operating complex systems designed for efficient collection and processing of cosmic resources. In the future, these natural cycles could serve as fundamental benchmarks for planning and conducting operations, enabling maximum efficiency and minimal energy expenditure. In October of the year 25, according to forecasts, the most favorable period for conducting such activities may occur, as during this time, long-term cycles of solar activity and magnetic field configurations will reach optimal parameters capable of ensuring the success and safety of the mission. Additionally, special attention is given to the composition of the solar wind, which transports various isotopes into space, atoms with neutron numbers differing from standard values. In particular, tritium, a lightweight isotope of hydrogen produced during thermonuclear reactions inside our Sun, represents a valuable fuel for advanced future reactors. Studies show that the solar wind carries tritium throughout the solar system. However, the concentrations of this isotope in solar wind streams are too low to be conveniently used by humans. Nevertheless, modern and prospective technologies for separation and concentration enable the extraction of significant amounts of tritium during planetary flybys or near-stellar approaches. This creates the possibility of using solar wind as a fuel source for new energy systems. Motivations for resource extraction from the space environment may go beyond simply obtaining fuel. In these extreme conditions, there are opportunities to mine and study exotic forms of matter and energy found only in stellar environments. Specifically, in stellar coronae, where temperatures and pressures reach levels exceeding all known terrestrial values, unusual states of matter can form and exist. The consequences for sound design during such operations provoke truly profound reflections and require a reassessment of conventional ideas about possible scenarios. In the vacuum of space, where there is no atmosphere and consequently sound waves cannot propagate, hypothetical resource extraction systems based on sound mechanisms lose their realism and practical applicability. However, despite this, electromagnetic signatures of such systems can create characteristic patterns that, when properly decoded, could be recognized by civilizations possessing the appropriate technologies. These signatures may manifest as slow low-frequency hums on radio frequencies, as well as distant crackles and faint electromagnetic oscillations. When magnetic field lines intersect, connect, or disconnect, the energy released is transformed into electromagnetic waves rather than acoustic phenomena, which determines their nature. To carry out any real resource extraction operation, constant monitoring and precise positioning of devices or mechanisms in the space environment are required. These tasks involve continuous regulation of orientation and attitude parameters to counteract the complex gravitational and magnetic forces acting near stars and other astronomical objects. Such requirements inevitably produce measurable signatures in the trajectories and rotational states of these objects. Modern instruments must be capable of detecting and analyzing such signatures if they are indeed present. The absence of such indicators in our current observations suggests that active resource extraction operations are most likely not underway or are being carried out using very subtle, barely detectable methods. Nonetheless, it must be acknowledged that our detection capabilities are limited, and we cannot rule out the existence of technologies that far surpass our knowledge and achievements. Systems capable of maintaining precise positioning and orientation through manipulations of local magnetic fields may operate with such delicate signatures that they remain beyond our current measurement thresholds. What appears to us as natural and characteristic behavior of comets, such as the visible ion tail directed away from the Sun, could, in fact, be masking or the result of complex technological protocols. These protocols might be so sophisticated that they create the illusion of natural activity, while in reality, they are controlled and purposeful interventions. Ethical questions related to resource extraction from stellar objects provoke a profound and complex discourse on rights, ownership, and territorial claims in outer space. If we assume that advanced civilizations regularly utilize stars for energy and material acquisition, then the question arises: is our Sun a common property of the entire galaxy, or does its presence in orbit constitute some form of territorial claim? How should resource extraction operations be viewed, as a right or as competition? And how should we respond to the possible emergence of developing civilizations similar to humanity? Consider them owners, potential rivals, or simply biological phenomena that do not influence the balance of power? In these considerations, the ability to distinguish genuine signs of resource extraction activity from natural behaviors of celestial objects becomes particularly important. Actual indicators of such operations might, for example, manifest as changes in the geometry and behavior of comet ion tails. Natural ion tails, directed away from the Sun, result from the interaction of solar radiation and the stream of charged particles, the solar wind, according to well-established physical laws. Any artificially conducted resource extraction activity must conform to these physical patterns or cause noticeable deviations in the expected geometry of the tails. Such anomalies could indicate interference or controlled operations. Regarding plasma behavior, our current observations show that ion tails observed in space conform to standard interaction models. The spectroscopic signatures we detect with modern astronomical instruments correspond to known molecular species present in space and undergoing typical chemical processes driven by solar heat. These signatures suggest that the molecules responsible for them are in equilibrium with their environment, and their presence results from natural physical and chemical reactions occurring in interstellar clouds and on the surfaces of celestial bodies. If active resource extraction operations from other stellar objects or asteroids were taking place within our solar system, we would undoubtedly find evidence in their orbital data, signs that differ from those characteristic of natural bodies. Such signs, known as non-Keplerian orbital signatures, would indicate that systems associated with these operations maintain their positions by regulating their movements and arrangements in response to changing solar radiation and gravitational influences. In other words, these systems would adapt to solar conditions, maintaining optimal points for resource collection, which would manifest as unusual orbital patterns. However, the absence of such signs in the collected data, both for the object known as triatlas and for another designated SW2, suggests that any forces acting upon these objects are primarily gravitational. They do not show signs of artificial control or the presence of advanced technological means specifically designed to create controlled trajectories. Nevertheless, the idea of resource gathering, or systems that turn cosmic encounters into elements of large-scale industrial enterprises, remains compelling. This concept is enriched by the notion that random collisions or close approaches to objects could be integrated into a complex, branching system that spans not only space but also significant periods of time. It implies that our Sun serves not only as an energy source for Earth but also as a component within broader, possibly interstellar or even galactic, economic and energy networks. These networks may operate on levels beyond our current understanding, and their scale is difficult to grasp through rational thought. As a result, the approach of celestial objects to Earth in October of the upcoming year 25 shifts from mere gravitational mechanics to an event of significant importance for space trade and resource exchange. And, what is particularly interesting, both of these objects, the Triatlas and SW2, play highly specialized roles in this situation, related to resource extraction and processing operations carried out according to pre-established schedules, which were set even before human civilization began to ponder the nature and origin of light. From this perspective, if we consider our Sun as a station or node within a broader galactic resource distribution system, the question arises: how many routes regularly pass through here, into our solar system, and what exactly do they carry with them into the endless cosmic night? The answers to these questions may perhaps be found in the fire and plasma of the solar corona, those bright and dynamic phenomena that can only be read by those possessing sufficiently advanced understanding, capable of distinguishing natural phenomena from intentionally created or assembled matter and energy in a specific sequence. It is in these bright flares and jets emanating from the corona that, most likely, clues are hidden about what occurs beyond our perception, about what is carried into space and what remains within our system. The second part of this narrative is dedicated to the game of conflict unfolding beyond our visible horizon, in a hidden theater where the dazzling brilliance of the Sun conceals secrets inaccessible to human telescopes, and all possible scenarios for the development of events remain in the realm of deep speculation. In October of the 25th year, the final act of this cosmic conflict, which has been ongoing since then, may occur. The appearance of the interstellar craft designated SWR2 near our Sun is becoming increasingly dramatic, representing not just another approach but rather an urgent and highly precise deployment operation. Its sudden and intense development of a tail, resembling a bright jet, conceals behind it swift and decisive actions to deploy rescue mechanisms and stabilization systems necessary for continuing the mission or saving the crew. The trajectory of this massive object, similar to that of a comet, predisposes it, at the critical stage of its approach to the Sun, when thermal and radiation stresses reach their peak, to intercept or even delay other objects, such as 3 satellites of the Atlas type, which is especially important when facing dangerous conditions. At this moment, when thermal stress and radiation could destroy any remaining operational systems aboard the damaged interstellar ship, a precise and coordinated rescue operation is essential. Organizing such rescue missions requires exceptional timing and flawless coordination of actions, with everything designed to appear as a natural and inevitable manifestation of gravitational mechanics, so as not to arouse unnecessary suspicion. SWR2 will need to approach the object in a manner similar to the movement of celestial bodies under gravitational influence, at a specific speed and along a chosen trajectory, matching the motion of the third Atlas-type satellite. At the same time, it deploys systems designed for collection and disguising themselves as underground eruptions, allowing it to remain undetected. This operation may involve transmitting critical systems, evacuating data from storage units, or providing power and life support systems for crew members who have survived years of interstellar travel but encountered system failures precisely during the final approach to our star. There is also an alternative perspective suggesting that SWR2 is not merely a rescue device but rather a collector of information or equipment. In this case, its task is to gather data or extract the probe's equipment after completing its mission. In this scenario, the third Atlas-type satellite could serve as an intelligence platform intended to obtain specific information about our solar system, while SWR2 functions as a mobile storage and transport system that delivers collected data back to the origin point. The extraction process might involve physical interaction between the devices, which, from an observer's point of view, could appear as a collision or fragmentation, but essentially, it would be a successful recovery of reconnaissance assets after mission completion, not their destruction. This unusual moment of proximity between both objects and the Sun creates optimal conditions for data transfer and physical recovery, while minimizing the risk of detection and observation by ground-based telescopes and radio telescopes. The logistics of such an interstellar information-gathering operation involves a phased approach, utilizing specialized reconnaissance probes, single-use devices designed for one-time missions, after which their functions are considered fulfilled. The energy costs of interstellar travel are extremely high, making it economically unfeasible to return small devices to base after a mission. Instead, larger data collectors are capable of efficiently gathering information from multiple completed missions, following trajectories that ultimately allow them to return to their original platform or base. On the opposite end of the spectrum is a scenario predicting the most grim interpretation of the October approach. In this case, SWR2 is not intended to assist the 3LES type object but instead acts as a means of erasing traces of its passage through our solar system. Under this hypothesis, the interstellar visitor is something akin to a beacon or communication platform that has malfunctioned or exceeded its operational parameters. It is possible that it is transmitting information to its controllers or even revealing too much about its artificial nature, as evidenced by its behavior. Within the current plans and strategies, SWR2 is transformed into a specialized unit tasked with conducting emergency operations to clean up and destroy traces of technological visits carried out on our planet, in order to make it as difficult as possible or entirely impossible for an evolving human mind to gather sufficient evidence of the artificial origin of these traces. This cleanup operation must not only eliminate any remaining tracks left by 3ATLAC but also include a set of measures to disperse its debris and fragments in such a way that any forensic analysis or reconstruction of events related to this object becomes impossible. Advanced technical means and destruction methods allow the probe to be broken down to its atomic components, dispersing its parts so thoroughly that no signs of its artificial placement or structure remain. The timing of such a hypothetical sanitary operation is carefully calculated, taking into account human observation capabilities and the decay processes of observation, when both the probe and its debris are exposed to sunlight and become less detectable by observation tools. Since the cleanup operation is conducted at a time when ground-based telescopes and other observation means cannot detect the process, the team responsible for disposal ensures that no human instruments record the moment of actual destruction and reduction to nothingness. As a result, evidence and proof vanish without a trace. Each scenario related to such an operation requires us to reconsider the impressive phenomena we observe as bright comet tails and expanding cosmic objects, often reminiscent of camouflage operations associated with technologies operating at the edge of physical and engineering principles, which remain incomprehensible to us for now. These bright tails and comets, with their extraordinary flickering and expansion, could be masking energy weapons, matter destruction systems, or even exotic propulsion systems that manipulate interactions between solar wind and magnetic fields. However, such dramatic interpretations must be aligned with continuous observational data, which show no signs of conflict, coordination, or artificially induced interference. Both objects continue to follow trajectories determined by gravitational laws, displaying spectroscopic signatures characteristic of natural processes such as ice sublimation and dust emission, which fully correspond to natural phenomena. No anomalous accelerations or deviations indicate active maneuvering or attempts to change course. There are also no recorded electromagnetic signals or emissions that could indicate the presence of artificial energy systems or communication equipment embedded within these celestial bodies. In this context, Mars serves as our only potential witness capable of detecting possible events during critical phases of close approaches, especially at moments when objects pass nearby or cross orbital trajectories. Currently, the orbiting spacecraft around Mars are tuned to monitor the passage of three objects known as 3ATLAC during their flyby, scheduled for October 3. These robotic satellites are equipped with instruments primarily designed for studying planets and their characteristics, rather than detecting exotic or unusual cosmic phenomena. Nevertheless, they are capable of recording any signs of interaction that go beyond natural behavior, for example, sudden trajectory changes, unusual energy signatures, or anomalous emissions. Coordinating observations of these objects through the Martian orbital systems managed by the European Space Agency is our reliable hope to maintain continuous monitoring and observation, even during times when ground-based telescopes cannot observe due to solar glare or other conditions. However, the existing technical limitations of the Martian spacecraft mean that, at great distances, they can only detect the most luminous events. Signal transmission delays between Earth and Mars significantly complicate the task of monitoring events occurring there, especially when real-time response is required. The signal travel time in this space ranges from 12 to 24 minutes, meaning any attempt at intervention or response from our planet will be delayed so much that it will no longer influence the development of events unfolding over minutes or hours. As a result, we find ourselves in the position of passive observers, deprived of the ability to intervene promptly in processes occurring at a distance, where even our quick reaction cannot compensate for the substantial signal delay. Everything happening in the space between Mars and our Sun remains outside our direct control, and we observe it as if witnessing someone else's game, unable to influence the outcome. The psychological appeal of conflict scenarios, arising from mental modeling of cosmic collisions or encounters between intelligent beings, is largely explained by human tendency to interpret ambiguous situations through familiar narrative structures. In our culture, such situations often take the form of a struggle, a fight for survival, conflict resolution, and ultimately, the triumph of one force over another. These dramatic frameworks create a special emotional satisfaction, allowing individuals to ascribe meaning and purpose to chaotic and complex cosmic events. Even when these scenarios involve destruction rather than creation, when the light returns and our telescopes once again have the opportunity to observe both presumed visitors, the question arises: do the objects that disappeared beyond the boundary of our solar system still exist? Will their orbits, composition, and behavior match the predictions based on natural comet models? Or will we encounter unexpected evidence that conflicts and their resolutions occur in the universe on scales that surpass human experience, challenging our understanding of how far reason can extend when acting beyond the limits of observation, penetrating the depths of cosmic processes? A period can be called the October silence. As the instruments designed for observation gradually fall silent one after another, the entire cosmic scene plunges into quietude. When both objects are bathed in the blinding light of the sun, signals from our observatories begin to flicker and fade, as if disappearing into the fathomless depths of space. Coronagraphs, tools used to block out sunlight, become overwhelmed by bright light, and this grand scene, once among the most majestic spectacles in our nearby cosmic neighborhood, vanishes behind a veil of hydrogen flames. In this backdrop remain only dark memories, guesses, and a quiet countdown measured by atomic clocks, ticking off seconds until the next revelation. In institutions of government and university observatories around the world, astronomers hold their breath, experiencing moments of uncertainty. Social media buzzes with activity. Enthusiasts and professionals share theories, artistic interpretations, and hypotheses, trying to understand what lies behind this silence. The lack of data becomes a kind of fertile ground for the most fantastic assumptions, expanding the boundaries of human imagination. In this forced silence, every scenario seems equally valid. Each version of events holds its potential truth. Before our eyes unfolds a palette of possible outcomes, like frames from an unfinished film, where each moment could be the finale or the beginning of a new story. One object suddenly reappears, altered in color or brightness after its encounter with the sun, forever transformed by this cosmic collision. Another, on the contrary, appears less bright than expected or not at all, absorbed by forces we cannot measure or comprehend. Perhaps coronagraphs will reveal fragile rings made of fragments. The peak of the so-called public observation window for Comet SR2 occurs in late September and October. It is during this period that astronomy enthusiasts have the best chance to admire its impressive tail, which will brightly and dramatically stretch across the evening sky, decorating the night with its mysterious glow. At the same time, if our astronomical models are confirmed, this comet, designated as 3IATL, will emerge from solar conjunction in December, a position where it aligns with the Sun, temporarily making observation difficult. After this event, professional astronomers will be able to resume detailed studies of its chemical composition, analyze the features of its orbital evolution, and track changes occurring as the comet approaches and recedes from the solar system. Modern data increasingly suggest that the origins and behavior of these two remarkable comets are actually natural, not the result of mysterious or mystical factors. Their temporal coincidence is a phenomenon caused by the laws of orbital mechanics, not evidence of a complex choreography of intelligent forces. This is the scientific value of observation. We are not trying to confirm our boldest hypotheses about the cosmos, but to understand the processes of star system formation, investigate the chemistry of primordial materials brought from distant corners of our galaxy, and comprehend the physical mechanisms that govern the development of objects exposed to the intense radiation of our Sun. However, between moments of observation and interpretation, between collected data and their understanding, there are periods of silence in which new stories are born and flourish. It is precisely during this silent interval that we, humans seeking patterns in the boundless universe, awaken to new reflections. The universe, so vast and multifaceted, simultaneously encompasses the simplest physical laws and harbors incredible possibilities. The October pause becomes a kind of canvas on which we project our deepest questions about consciousness, the purpose of existence, and our place within this cosmic order, which seems both infinite and mysterious. Contemplate a hypothetical scenario: if an ancient machine, one that could exist in legends or fantasies, were to arrange a meeting with our Sun, what would it discover in our tiny corner of the universe? A young and emerging world, inhabited by curious beings just beginning to reach out toward the stars, already fills the electromagnetic spectrum with the noise of its civilization. Perhaps this world will find exactly what it seeks, or, conversely, it will discover something unexpected within the complex symphony of human hopes and fears played out against the backdrop of infinite cosmic time. When December returns our observers the ability to once again monitor celestial bodies, when the instruments resume their work, whispering about the positions, velocities, and spectral characteristics of comets and planets, we will find the answer to a question that has echoed through many of our reflections, in 14 chapters of wonder and speculation. This answer may be a comet, a fortress, or perhaps an enigmatic response to the mysteries of the universe. For now, we remain in October silence, as if embraced by the gravity of our Sun, pondering what stories darkness might write in languages we have yet to learn to read. After all, the universe guards its secrets very carefully, but patience and perseverance will surely be rewarded with revelation. And in this calm and anticipation, our understanding, discoveries, and new horizons are born, promising to unfold in due time. May this night bring peace and silence, for it is in these that the deepest thoughts and ideas are born. Good night.